Thank you very much, and thank you for the invitation to give this seminar. And yeah, I hope everyone is weathering the pandemic as best possible in this horrible time. So what I'm going to be discussing today is some aspects of scattering in de Sitter space. In particular, some new techniques that we've been developing to study them systematically. And I'll be speaking mostly about work that was done in collaboration with Massimo Taronda. And yeah, so that it doesn't feel like I just talk to myself for an extended period of time, please interrupt me at any point if you have any question or if I can provide some clarification. And I will also try to pause at various points to take questions. Okay, so let me start. Okay, so the imprints of scattering processes that take place in a de Sitter spacetime are encoded in correlation functions on its boundaries at infinity, which, as I record here on the slide, are spatial slices in the very far past and in the very far future. So if you like, these are like the analogues of the S matrix elements. So there are various reasons why it might be interesting to study these types of observables. So for instance, this provides us with an example of holography where time is emergent. So instead of only just space, like in the plain vanilla ADS CFT setting. So this is a step away from the relative security of the ADS CFT correspondence in a direction where we might potentially learn something fundamentally new about holography itself, so like the emergence of time. While at the same time, this setup retains some familiar features that we might look to for reassurance or try to take advantage of. And one of these that we will see in this talk is the fact that these boundaries at infinity are conformal. So the corresponding observables are constrained by conformal symmetry, just like in ADS CFT. And let me stress that this statement is purely about kinematics and doesn't rely on the existence of a dual description given by a concrete conformal field theory. So in this talk, I'm going to focus on processes where all of the external legs lie on the boundary at future infinity. So these observables are of particular interest from the perspective of inflationary cosmology, which, as we know, postulates that the very early universe is a period of rapid expansion, and this can be described by the de Sitter spacetime. And one of the main predictions is that spatial correlations at the end of inflation, so on this grey spatial slice here, so say the scalar or the tensor fluctuations, the prediction is that as time evolves forward, these correlations give rise to correlations, for instance, in the CMB and the distribution of galaxies. So this would make inflation the highest energy observable natural process, where in particular the energy or the Hubble scale during inflation could be as high as 10 to the 14 GeV. So because of this, inflation presents us with this really incredible opportunity to try to probe the laws of physics at these scales, which so far remain somewhat elusive. And the task that we have ahead is to classify the effects of new degrees of freedom that might become observable at these scales. So in particular, to classify the imprints of possible processes that can take place, for instance, here in these question marks. And this is in order to compare with future observations of these guys. So what I've just described is what is often referred to as the cosmological collider physics program, and this has been pioneered by numerous groups, some of which I put here on the slide. And this is essentially where we view the inflationary expansion as this insane high energy particle collider. So in order to reach the goals of this program, we need to develop systematic techniques, not only to blindly evaluate these boundary correlation functions, but also to try to gain a better understanding of their structure. And although, of course, we don't have an understanding which rivals that which we have for scattering amplitudes in flat space, in recent years, there has been significant progress in this direction, which nonetheless draws inspiration from the successes and the strengths of the scattering amplitudes program. But key steps have been taken, for instance, by these groups here on the bottom of the slide. So in a similar way, it's worth noting that many of the goals of this cosmological collider physics program are in some way shared by those in the parallel program in anti-de Sitter space. So in ADS, we have a pretty good understanding of the structure of boundary correlators, not only at tree level, but also beyond. And in ADS, we have a bit of an edge compared to flat space because we can make use of the ADS CFT correspondence, where in particular, all of our questions and confusions about observables in asymptotically anti-de Sitter can be translated to sharp questions about the consistency of correlation functions in conformal field theory, which are defined in terms of conformal symmetry, unitarity, and a consistent operator product expansion. So a natural question to ask at this point is if any of the techniques which led to this type of progress in ADS can be adapted to De Sitter. And this question is not too unreasonable because at the end of the day, many of these techniques were developed in Euclidean ADS, mostly because life is simpler in Euclidean signature. And Euclidean ADS shares the isometry group with the De Sitter spacetime, so it wouldn't be too shocking if it does turn out that there are things that carry over. But despite these similarities, there are also major differences. And one of these, of course, is that the De Sitter background is time dependent. So if you want to compute fixed time correlators like those that we're interested in on the boundary at future infinity, the standard framework that you have to use is the so-called Schwinger-Keldysh or in-in formalism. So this is where you have to pay an extra bit of attention when you evaluate the bulk time integral. So you first have to make sure that you integrate in a time-ordered fashion along the so-called plus branch of the in-in contour. And then once you've done that, you have to not forget to integrate back in an anti-time ordered fashion along the so-called minus branch of the in-in contour. So these differences with respect to what we're used to in Euclidean ADS, they make at least a direct application of many of those techniques far from straightforward, at least in the current way that they are formulated. So one of the main objectives of the work that I'm going to tell you about is to see if there is some way to level the playing field between boundary correlators in these two spacetimes. And to this end, we found it rather effective to adopt a type of Mellin-Barnes representation for boundary correlators in momentum space. So we know that Mellin-Barnes integrals are contour integrals which involve products and ratios of gamma functions, where the integration contour is usually taken to run parallel to the imaginary axis. So if you have some boundary correlator describing like a scattering process in a bulk spacetime, in this Mellin-Barnes representation, each external leg in this scattering process, say with some boundary momentum.
Sorry, Charlotte, could I ask? Could you say a little more what you'll be computing in De Sitter space?
So we're computing, so we're not computing wave function coefficients. So we're not doing like what, so if we were computing wave function coefficients, then we would just take these ADS objects and wick rotate directly to De Sitter. So we're computing the vacuum expectation value. So we're extrapolating correlators in De Sitter to the boundary at future infinity.
So classically, are you computing an action as a function of boundary values? And if so, with what boundary conditions inside?
No, that would be more the wave function coefficient, right? If we were computing action with boundary values.
Okay, so just classically, forgetting loops and so on, what would you be computing classically? What classical problem are you trying to solve?
So we're just computing the in De Sitter correlator. So we're just computing fixed time correlations in De Sitter of operators, and we're taking the boundary limit. And so the boundary condition is fixed by the choice of vacuum at early times. So this fixes the behavior of your fields towards the boundary at future infinity. It's not like the wave function where you fix the behavior, like in ADS CFT, where you fix the behavior of your fields at the boundary, we're fixing the behavior of the fields towards the boundary by the choice of vacuum at early times.
I see, thank you.
But sorry, Charlotte, if I can ask you,
Yes.
Because for example, in the program we developed also, you know, the wave function is a more natural object, I would say, in that the symmetries are more manifest actually in the wave function itself. And at least what we found was, and there was a lot of confusion in the cosmology literature, which got clarified by first working with the wave function. Because when you go to expectation values from the wave function, you often have to further gauge fix, etc. And some of the symmetries get more muddled up. Right.
Yes, yes.
So I was wondering why you find it more. Actually, I had this question even in your strings talk.
Yeah, I wasn't understanding you. Yeah, but
it was a very nice talk. But I had this question then also, which is, why do you find it more convenient somehow to work directly with the expectation values? Somehow, maybe I'm biased by ADS CFT, but even in DS, we found the symmetries and all just are easier for us to understand, and the word identities for the wave function itself. So anyway, just thought I'd ask you.
Well, to us, I mean, honestly, like if I have to be really honest, we kind of wanted to bypass the wave function coefficient because the in correlators were the things that cosmologists compute. So when we started the project, already we were kind of geared towards computing in correlators. And then we found these nice relations between like the actual in propagators with those in anti-de space. And in the wave function, you can use some of the techniques that I'm going to describe, but for instance, it's not clear. I think Toshifumi was mentioning this in my talk in Springs, that it's not clear how to get like bulk propagators for the wave function from the ADS counterparts. There's some subtlety that I also haven't yet understood, but he was trying to tell me this type of thing. So it kind of came out, I don't know, these relations that you will see as the talk, and also as you saw in the strings talk, they come out more naturally if you go directly to the in correlators.
Yeah, it's a bit, well, I look forward to hearing your talk here as well, but it's a bit strange because, you know, as Shiraz was also saying, and this is what we found, that if you just compute for, of course, a particular choice of boundary conditions, just the action in de Sitter with some late time boundary values, then you naturally get the wave function, and that maps naturally to the ADS partition function, right? So in a sense, the map is much more natural between the wave function and the partition function of ADS. So it's interesting for me that you find it, in a sense, more natural to do the expectation values, you know, but anyway.
Me, I mean, honestly, I haven't paid a great deal of attention to the wave function because we kind of got on this track. So I haven't made a really concerted effort to extend our computations also to the wave function. But as far as I understood, as I said, it's not clear whether these nice relations between propagators and the bulk propagators hold at the level of the wave function. So, but I would like, this is something that I would have to sit down and work out the details. But yeah, it's not clear. Maybe what we're doing is better to do in wave function. It's not clear.
That's fine. Thank you.
I'm sorry to slow you down. Can you just say again, what do you mean by in, please?
So when you do the bulk time integral, for instance, the boundary condition is fixed by the vacuum at early times. So what you do is you integrate first you start the integral from early times in the bulk time integral, and then you integrate to the time that you're interested in. But during this point, the vacuum may have changed, so then you have to integrate back to the early time again. So the in state is the vacuum at early times, and then you go back to in. So that's why it's called in. So you integrate from the initial time to the time that you're interested in, and then you go back to the in state again. So instead of in out.
So it's like an expectation value in a density matrix, which is vacuum.
Yes.
Or even a state, Shiraz, but that's right. I mean, you just take a state at some time t, obtained by evolving from, say, the far past, as Charlotte is saying, then compute your expectation values in that state. So, I mean, in terms of path integral, you have to get up to that state, you know, put in your operators and then go back from where you started, right? So it's not a in-out S matrix, but an in expectation value, right? As Charlotte is explaining.
Yeah. Okay. Okay, like, what was I saying before? So in the Mellin representation for these boundary correlators, if you have some external leg with some boundary momentum Ki, in this Mellin-Barnes representation that we defined.
I'm sorry, Charlotte, to keep stopping you, just to make sure I completely understand. So classically speaking, is this saying that your state at the beginning, your classical configuration at a very early times was just the vacuum?
Yes.
And then you evolve to wherever you go?
Yes.
Thank you.
And then let me interrupt you again, sorry, but now I won't, which is, will you work with the Bunch-Davies or you can work with a general alpha vacuum as well, Charlotte? I mean,
this is so in the formalism that we derived, there is a control over the choice of vacuum at early times, but in all of our explicit computations, we restrict it to the Bunch-Davies.
Thank you. Go ahead.
Okay, so yeah, in this Mellin representation, if you have an external leg, this is described by what I call a single external Mellin variable SI. So where this boundary momentum Ki enters the Mellin representation in the way that you see here on the slide. So we have an exponent that is fixed in terms of the external Mellin variable SI, as well as the scalar dimension delta plus of the corresponding operator on the boundary. And each of these external legs, so each of these factors here, is accompanied by two infinite families of poles, which are the poles in the Mellin-Barnes representation of the corresponding external propagator, so the bulk boundary propagator. And this is a type of Bessel function. So I put these poles here on the bottom right. So they're integer spaced and they head off to minus infinity. So they're encoded in some gamma functions. And the location of these poles depend on the mass of the external particle, which enters in the usual way through the scaling dimension delta.
Sorry, Charlotte. Is this representation related to the Mellin representation at all, or this is a?
It's different. Yeah. So this is this, for instance, it's not what you would get if you Fourier transformed the usual Mellin amplitudes in position space. So you could think of this as like, yeah, you can. So we know in momentum space that bulk boundary propagators are Bessel functions, and this is just literally taking the Mellin representation of that Bessel function. This is why you get a single Mellin variable for each external leg, for instance.
So but the final is going to be your Mellin-Barnes representation. The object that you would be working with is a function of S, K, and S. Sorry, S and also K.
Yes. Yeah. So you could, this is like what I'm going to explain in the following is like you can regard kind of like this S is like together with the momentum. So kind of on the same footing. They have similar properties.
I see. And what are U's? Maybe, I don't know,
Sorry?
maybe we'll see. There are U's also in the integral.
Yes, you will see them in a moment. Yeah. The U's are for the internal legs. Yeah, you will see them in a moment. Yeah, so these basic features that I just outlined, they actually become rather suggestive when you note that just like how translation invariance enforces momentum conservation, the dilatation ward identities that are satisfied by conformal correlation functions, they imply a similar constraint on the external Mellin variables. So they have to sum up to a constant, and you will see some examples of this constant in a moment. And just like how the momentum conserving delta function arises as an integral over position x on the boundary, the delta function that enforces this constraint on the external Mellin variables can be expressed in a similar way as an integral over the bulk radial coordinate, which in Poincare coordinates, which is what we use in all of our computations, this is usually called Z. So these kind of parallels between momentum space and this Mellin-Barnes representation, they continue, and you will see more of them as the talk progresses. And to me, it makes it kind of tempting to suggest that this Mellin representation is some kind of natural habitat for conformal correlation functions in momentum space. But this statement we haven't substantiated beyond saying, there are these nice similarities between momentum representation and this Mellin-Barnes integrals.
So, sorry, I have a basic problem, basic question. So, I mean, usually, I should think of this as some sort of a transform, or, I mean, in a transform, you swap one type of variables for the other type of variables, right?
Yes.
But this gadget still has S as well as K. So it's some redundancies introduced in this blue boxed picture. In
some way, yes. So you can think of, one way I think about it is that, maybe we'll see a bit more of this later on, these boundary correlators, it's been shown that these are complicated generalized hypergeometric functions. So this blue box here is the Mellin representation of this hypergeometric function. So it's like the 2f1 can be expressed as a Mellin integral, like in the entire complex plane. And this is what this blue box is doing. But there is some redundancy, as you said. So if you want to make the integral nice and symmetric under permutations of the external legs, then you have to introduce this constraint here.
Roughly speaking, are these S's like Schwinger parameters in Feynman diagrams?
Yes. It's similar to this. Yeah. Okay.
Okay.
Sorry, Charlotte, just to understand, are you going to be computing these correlation functions at late time after the modes have exited the horizon and the correlators have become time independent, or are they for any general times?
You can, okay, so these external Mellin variables here, but yes, in order to use a single external Mellin variable, I've already taken the limit of late times.
Okay. Okay.
There is a little bit of control over the late time cutoff, but I think you would miss some terms if you just restricted to this single external Mellin variable. Yeah, so you should safely assume that always assume that I'm working at the late time boundary.
Okay, thank you.
So yeah, the simplest type of boundary correlator is that which corresponds to a 3-point contact diagram. So these only have external legs, and there are 3 of them. So according to these definitions that I just outlined in this Mellin representation, it involves 3 external Mellin variables, S1, S2, and S3, 1 for each external leg, which accompanies each of the boundary momenta. Translation invariance enforces momentum conservation, and the dilatation ward identities require that these external Mellin variables sum up to this constant here, which you see depends on the boundary dimension D and the spins J of the fields that are participating in the cubic vertex. And that should be a J2 and this should be a J3. If you also have an internal leg, like in a 4-point exchange, in this Mellin-Barnes representation, each internal leg in this scattering process is described by what I call a pair of internal Mellin variables, U and U bar, where the internal momentum or exchange momentum, K capital I, enters the Mellin representation the way that you see here. So we have an exponent that depends on these internal Mellin variables through their sum, U plus U bar.
Sorry, I'm a bit confused. This K's are momentum in the boundary theory, right?
Yes.
Then what is this K capital I? Because that's supposed to be some momentum in the ADS?
No, it's still on the boundary. Yeah, so it's usual, like here.
Okay.
So no, these are purely, this is like computing your Witten diagram in Poincare coordinates, and you take the Fourier transform with respect to the boundary directions. And
sorry, I think I had a similar question. Sorry, I thought, I probably missed it, but I thought in your previous slide, you were just taking CFT correlators and performing some, giving us some representation of that.
Yes.
Now you've introduced these points in the bulk. So that's natural from the point of view of ADS CFT, but if you just had a CFT, what are these bulk points? What are these?
You mean
yes.
These bulk points here?
Yes.
So my CFT correlators are, I'm taking like the large N limit, and I'm assuming that I can organize this in terms of Witten diagrams in the bulk. Okay, so now we're in a bulk. Is it right that in the previous transparency, everything you said did not require a bulk? No, it doesn't actually. So for instance, yeah, so you can kind of think of these, it's kind of a dual way to thinking about it. So these Mellin, so you have, the triple K representation of 3-point conformal correlations in momentum space. So like by solving the conformal ward identities, you know that your 3-point correlator has to be some integral over these free Bessel functions. And these Bessel functions turn out to be, because it's kinematics at the 3-point level, they turn out to be bulk boundary propagators in the bulk. It's kind of, this is what we're doing here. So these Mellin variables here are the Mellin representation of these Bessel functions. So you can kind of think of, some way I try to think about it, but I don't know how rigorous it is you can try to think of this external Mellin variables as some natural object that would replace like momentum in the radial direction. So you can try to think of these Mellin variables and also these U and U bar that you see on the next slide. There's some kind of like momentum in the radial direction. But these here are purely on the boundary.
Sorry, but just to completely understand, this diagram makes sense only when you have a local bulk theory. Is this right?
Yes. Yes.
Okay, thank you.
Yeah.
The conformal ward identities are not solved yet, right?
At the 3-point level, yes. Here, no, here also they are solved.
I mean, the fact that the correlator in position space depends only on the cross ratios. What would be the analogous statement in this language?
I think here I'm just assuming that the exchange itself has to be a solution to a certain class of conformal ward identities. So in that sense, in restricting to saying that I want in making the statement that I want to study an exchange, I'm assuming that I'm studying a particular solution to the conformal ward identities.
Okay.
Sorry, Charlotte, you said this, but I didn't quite understand it. So just from the bulk point of view, say in de Sitter space, you were saying the Mellin variables SI can be thought of as some momentum, say, corresponding to the radial direction. Is that right?
I mean, we didn't make it rigorous at all, but this is some way to try to think about it. Like these Mellin variables could be some kind of natural replacement of like the momentum in the radial direction.
I see. So, I mean, the Bessel functions, let's say if we were working with standard Poincaré coordinates, you would get Bessel functions in the bulk, and then you would have the bulk radial variable Z, as they call it in Poincaré coordinates, or anyway, the bulk radial variable, and this would be some momentum transform of that, or the analog of that.
Yes, yeah, precisely that. But yeah, this is the way I like to think about it, but I haven't really made this rigorous, but this is some way I think about it.
Okay, thank you.
Yeah, okay, and so coming back to the Mellin representation, like the components of the Mellin representation of an exchange. And so just like how the exchange momentum Ki on the boundary is related to the external momenta, for momentum conservation at a cubic vertex, these internal Mellin variables U and U bar, they're related to the external Mellin variables through the constraint that we saw previously for Mellin variables that are connected via a cubic vertex. So what we found is that by adopting this Mellin representation for boundary correlators in momentum space, we found that this in some ways places their computation on a more equal footing. And the key observation is that propagators in this framework take a universal form, and they are constructed out of 3 basic building blocks. So if we focus first on the bulk propagators in Euclidean ADS, first building block is the corresponding harmonic function. So it's a solution to the corresponding source-free equation of motion. And this means in the Mellin-Barnes representation of this harmonic function, which involves 2 of these internal Mellin variables U and U bar, the poles in these U and U bar, their residues, because it's a solution to the source-free equation of motion, the residues of these poles generate the contribution from the physical exchange single particle state. Where the boundary condition is enforced by this middle building block, the yellow one, which is a linear combination of these functions, omega d and omega n, whose role is respectively to implement the Dirichlet-Neumann boundary condition. The most general boundary behavior is, of course, a linear combination of the 2.
I'm sorry, some elementary thing I didn't understand. I mean, normally propagators have sources at their insertion points.
Yes.
What do you mean by source free here?
And so I'm solving this is like the on-shell propagator. This is the equation for the on-shell propagator.
The on-shell propagator.
Yeah, so where you would get rid of the source and you just have this.
Thank you. Thank you.
But yeah, as I move on, we do make sure that the full propagator in the end does satisfy the equation of motion with a source. Okay, so yeah, these functions omega d and omega n, they're entire functions of these internal Mellin variables, U and U bar. So they don't contribute any pole to this Mellin representation. And as you can see on the slide, they have quite a simple form. So they have a factorized dependence on these internal Mellin variables, U and U bar. And as we will see later on in this talk, the zeros introduced by these sign functions, they overlap with the poles of the harmonic function, which would violate the boundary condition that you want to implement out of Dirichlet and Neumann. So these functions, omega d and omega n, they act as projectors onto the Dirichlet and Neumann boundary conditions. And we will see later on more concretely how this works in practice. So the final building block is this cosecant factor, and as is written, its role is to encode the contact terms in the exchange process. So the combination of the green and the yellow building blocks so far, they just satisfy the source-free equation of motion with some boundary condition. And this cosecant factor ensures that the full propagator satisfies the equation of motion with a source. So if you put the internal leg on shell, so if you take the cut or the discontinuity with respect to the internal momentum, this cosecant factor gets completely cancelled. So this expression here is the expression for the on-shell propagator. So this equation here tells you that you can reconstruct the full bulk propagator, which satisfies the equation of motion with a source, from its on-shell counterpart by multiplying with this cosecant factor here. Is this clear? Any questions at this point?
Sorry,
go ahead, Nili.
My question is, in the ADS CFT point of view, when you say that there is a possibility of a Dirichlet and Neumann, and when I'm considering a bulk-to-bulk propagator, what do I mean? Like, where are these propagators, these boundary conditions imposed?
Where they are imposed, the boundary conditions?
Yes.
So it's at the boundary. In Poincare coordinates, this would be z equals 0.
But we are talking about bulk-to-bulk propagators.
Oh, okay. So it's fixing yes. So it's so it would be if you took the boundary limit of one of the bulk points, then this would give you a particular like Dirichlet Neumann behavior at the boundary.
I see.
You could give it in this way.
And you, at this point, you would say that this alpha and beta is not arbitrary, because depending on what boundary condition I choose, if I would like to respect conformal symmetry, I mean, either alpha, beta, or some specific combination of them, like Robin boundary, whatever. So that has to be imposed. Otherwise,
at this level, these coefficients alpha and beta, they are arbitrary, because the Dirichlet Neumann boundary conditions is the most general solution that respects conformal symmetry at the boundary.
I see.
And yeah, I mean, if you want to, yeah, then you can choose one, like them to be 0 or a specific choice depending on, yeah. But of course, there are only some cases where it makes sense to choose a Neumann boundary condition to preserve unitarity, for instance. But yeah, this level, these coefficients are arbitrary.
So is this on-shell correlator the flat space analog of stripping off the poles?
Yes.
Okay, and so you get this on-shell, you can go between on-shell and off-shell by multiplying by 2-point functions going to that point boundary.
Sorry?
In flat space, you can go from the full correlator to the on-shell correlator by stripping off a pole, but a pole is just a 2-point function.
Yeah.
So you go from on-shell to off-shell by multiplying appropriate factors of 2-point functions.
Yes.
Is that the same thing here?
No, it's not quite the same. Okay, I haven't thought about it in this way, but naively, I would say that it's not the same. It's this cosecant factor. Yeah, it's not a. Yeah, I'm not sure.
Okay, thank you.
Okay, yeah. So this is the form of bulk propagators in Euclidean ADS. So moving over to de Sitter, within this in formalism, to each field there is associated 4 propagators, since the 2 points in the propagator can each sit either on the plus or minus branch of the in contour. So yes, there are 4 in total, because this can be plus or minus, and this can also be plus or minus. And each of these propagators take the same form as their ADS counterparts. So they're built from analogous building blocks which have the same role as those in ADS. So these projectors, omega D and omega N, they have exactly the same form. So they have this form here on the previous slide. Where now their interpretation is that they're projecting onto a given late time behavior of the exchanged field. So delta plus or delta minus, where the precise linear combination of the two is selected by our choice of vacuum at early times. And for the Bunch-Davis, if you want your propagator to correspond to that in the Bunch-Davis vacuum, then you would take these choices for the coefficients alpha and beta appearing in the propagator here. So the crucial bridge between propagators in these two spacetimes is that at the level of this Mellin-Barnes representation, the harmonic function in de Sitter, so which is this guy here, at the level of this Mellin representation, it's given by its ADS counterpart that we saw 1 or 2 slides ago, multiplied by 2 very simple phases. And these are associated to each point in the harmonic function. So as you can see, the sign of this phase depend on which branch in contour that the 2 points in the harmonic function sit on, so plus or minus hat. And you can establish this relation actually by analytically continuing from ADS to DS. So you can take your harmonic function in Euclidean ADS in Poincare coordinates, and you establish its Mellin-Barnes representation, which involves U and U bar, and then you Euclidate to Poincare coordinates in de Sitter. And quite nicely, the direction of rotation, so clockwise or anti-clockwise, dictates whether you land on the plus or minus branch of the in contour in the sitter. So if you take the boundary limit, you get also bulk boundary propagators. And for a given boundary behavior, which I just call here delta, so delta, this level can be delta plus or delta minus. In the same way, a bulk boundary propagator in the sitter is given by its counterpart in Euclidean ADS multiplied by the same type of symbol phase, where again, the sign of this phase depends on which branch of the in contour that your point in the bulk boundary propagator is sitting on. Okay. So these observations, they're quite significant because they tell you that the boundary correlators in ADS and DS, they differ by a simple collection of phases. So this framework provides a way to extend techniques and results from ADS to the sitter in quite a concrete way, as we will see. This framework also provides us with a new systematic understanding of boundary correlators in momentum space, whereas we'll see constructing boundary correlators in this framework just amounts to combining together these basic building blocks that we just seen it in a consistent fashion.
Charlotte,
yes?
These phases are coming from these K to the S type factors?
Sorry, I didn't hear.
These phases are coming from the K to the S type factors that were that you showed in some other slide.
Yes, so, like if you think about the, for instance, bulk boundary propagator in Poincare coordinates, so you would have like, in its Mellin representation, you would have K to the S and also Z to the S, for instance. And you can analytically continue to de sitter in two ways. You can either, as you said, you can wick rotate the momentum or also Z. So if you do either of those, then you get precisely this phase, so precisely as you said. Yep. Any more questions before I move on to the rest of the talk?
Yes, sorry. If you just took the Euclidean propagator and analytically continued without putting these phases, does that give you some propagator, perhaps not the some correlator, perhaps not the in correlator in the sitter space?
Do you mean if I don't think I fully understand. So you're saying, because that's precisely what we did. We took the Euclidean propagator and we wick rotated, and we had just identified. So from the anti-continuation, you can pull out these phases, and again, and then the thing that is left over is just the original propagator in Euclidean ADS. So
I see. So sorry. So maybe I misunderstood, but I thought you were saying that the bulk to bulk propagator in ADS is not in Euclidean ADS. You take that, you analytically continue that. You don't get quite the bulk to bulk in correlator in the sitter space, but you need to do some phase dressing. Is this?
Well, actually, what we're saying here is, so I'm not. This is crucial. So if you take a bulk propagator in ADS, the analytic continuation will not be like a good bulk propagator in the sitter. Instead, what we are doing is we are taking the harmonic function, and we are analytically continuing that. And after you've done that, you can then multiply by these projectors, which kind of impose whatever vacuum that you want to work in the sitter.
Okay. Thank you.
Yeah, so in this talk, I'm going to outline how we put these ideas.
Sorry, Charlotte, just maybe one more. I'm sorry. But suppose you were interested not in these in correlators, but in Feynman type, time-ordered correlators in the sitter space for whatever reason. Would they come about through a similar procedure?
Yes. So the plus propagator, for instance, is the Feynman. No, yeah, it is the Feynman propagator, the plus. So it's the time-ordered.
So you've done everything in one shot here.
Yes.
Okay. Thank you.
Okay, so in this talk, I'm going to explain how we put these ideas into practice whilst keeping our feet firmly anchored to the ground. So I'm going to stick to tree-level stuff throughout. And we'll start off with the 3-point contact diagrams, which are the basic building blocks from which we can construct more complicated observables. And we'll see using this Mellin formalism, you can immediately express a 3-point contact diagram in the sitter in terms of its counterpart in anti-de sitter space, for which expressions are available for any triplet of particles, so any mass spin and cubic coupling that connects them. We'll then move on to exchanges, and we'll see how, given the knowledge of the constituent three-point contact diagrams, the Mellin formalism itself makes it quite straightforward to implement the basic consistency criteria that determine the corresponding exchange, tree-level exchange. And once I've outlined all of these results, we'll explore a little bit what we can uncover about exchanges and interactions in the city using this formalism. So as I just said, we can construct a contact diagram in the city starting from its counterpart in anti-city space.
Sorry, Charlotte, just to make sure that I'm understanding. So this S variable here, if I'm interested in late time behavior, late time insertion of all these points, then I should take some limit of the S variable, because finally I would want answer only in this transverse slice, right? As a function of only this transverse position or momenta. So what should I do with the S variable, or?
The S variable is it's kind of like we put this condition in by hand. So by ensuring that this S variable is what is corresponding to a book boundary propagator. So this limit Z goes to 0 is kind of already incorporated in the S's. So you don't have to get rid of them. These S's are necessary to describe these conformal correlation functions completely. The answer, or did I not quite understand the question?
So you're saying that's, is it true that then that this S variable is actually labeling a single particle state itself?
It's what, sorry?
Is it labeling the state?
Yes, so it's labeling the external leg. So it's I think the best way to think about it is like, the simplest example is like the phi cubed contact diagram generated by a scalar. And so in this Witten diagram, you would have like your three Bessel functions, which are the bulk boundary propagators. And you take the Mellin representation of these Bessel functions, and then you have some Z to the S associated to each leg. And then you integrate over this Z, which is an integral over power law from 0 to infinity. And this is what gives you the Dirac delta function that we saw earlier on, which you can interpret as a constraint coming from the dilatation ward identities.
Okay. Thank you.
Sorry, Charlotte, I'm going to ask you a very remedial question. Please forgive me, because I don't know this in formalism. Okay, so I'm just trying to understand your pictures, your diagrams. But what I would normally, I would have thought the in formalism has, a contour where you first go out in time, insert the operators, and then come back, right? As you were saying. Now, if you're trying to compute a correlation function like that after inserting some operators, I would have thought it depends, and you bring down some perturbation from the Hamiltonian. I would have thought it depends, you have two kinds of lines. Either you're joining the perturbations, to the operators along the time direction going out, or the one coming back in, etc. Right?
Yes.
Where is that information in the picture you now draw?
Yeah, okay, these pictures are maybe a bit misleading. So when I say that, when I draw these diagrams, I'm just saying, okay, I'm taking, this represents a full contact amplitude within the in formalism, but technically you are right. I don't know if I drew it. Yeah, okay, so like for instance, technically I should write two diagrams, as you were saying. So here, for instance, this plus, I will be evaluating the time integral in a time ordered fashion. And in this minus, I should be integrating in an anti-time ordered fashion from the boundary back to the early time again, as you were saying. So yeah, these pictures maybe, they're a bit they're not scientifically accurate, maybe.
No, that's fine, that's fine. Okay, I was just trying to make sure I understand. Thank you.
Yeah.
Thank you.
Thank you for your question. Okay, yeah, so as I said, you can construct a contact diagram in situ starting from its ADS counterpart. And the way you go in the Mellin formalism is you take this Mellin-Barnes representation of your ADS contact diagram, which you can establish in your favorite way. In our papers, we took the Fourier transform of known results in position space and then massaged it into this Mellin-Barnes form. And once you have this Mellin representation of your ADS contact diagram, you multiply, in order to go over to the city, you multiply each external leg by the phase that converts it to a bulk boundary propagator in the city on a particular branch of the in contour. So this multiplying with this phase is what implements the wick rotation to the appropriate branch of the in contour in situ. So this gives you the contribution from that branch to the situ contact diagram. And so the overall phase that you get when you apply this procedure, so you get one of these phases for each of the 3 legs. And the overall phase that you get when you apply this procedure is a constant, because like we saw earlier on, the sum of the external Mellin variables is a constant by virtue of the dilatation ward density. So this is the constraint coming from the Dirac delta function that we saw earlier on. So this is the contribution to the de Sitter contact diagram from each branch of the in contour, so plus and minus. And to get the full de Sitter contact diagram, we have to sum the contribution from each branch of the plus and minus branches. And what happens is that these constant phases, they combine to give a constant sign factor that multiplies the corresponding contact diagram in anti-de Sitter space. So this sign factor is what is in some sense encoding the interference between the contributions coming from these different branches of the in contour. So like what can happen from this sign factor is that for certain values of d or scaling dimensions in the spin, the full de Sitter contact diagram can be vanishing even if its ADS counterpart is not, due to presence of a 0 of this sign function for certain values of these parameters. Another thing that can happen is that this ADS contact diagram might have a singularity, and this singularity might be cancelled by a 0 of this sign function, rendering instead the de Sitter contact diagram finite. And maybe a well-known example where this happens is if you have a conformally coupled scalar in ADS4. So if you compute the Witten diagram generated by the phi cube coupling, you find this has a singularity. And in this setting, this singularity is precisely cancelled by this sign factor, rendering the de Sitter amplitude, de Sitter correlator finite.
Sorry, Charlotte, I'm going to re-ask Abhijit's last question. Maybe he understood your answer, but I didn't. A 3-point function normally in, let's say, Euclidean de Sitter space would be labeled by, in momentum space would be labeled by 3 momenta and 3 dimensions, 3 scaling dimensions of the 3 operators.
Yes.
Your 3-point function is labeled by 3 momenta and 3 s's. So are your s's playing the role of dimension somehow?
The dimensions are still there here.
Okay, so then why is there one extra label? Why are the 3-point functions labeled by s's as well?
Because so implicitly, like if you want to get go back to like full momentum space, you would be integrating over these s's.
Okay.
So
so it's an intermediate step. It's not the final answer.
Yes. Yes. So I mean, okay, you could like view this Mellin space as some kind of, if you want to view it as some analog of momentum space, then we can work purely at the level of this blue box here, if you want. But of course, if you want to go back to what we're used to, physical momentum space with respect to the boundary, then you would have to integrate over these Mellin integrals.
Okay, thank you.
Charlotte, can I understand then this S is essentially, I mean, it's not quite time independent situation, but it's some sort of an energy, right?
Yes, yeah, precisely this. Yeah, this is some way that we try to think about it.
So in that sense, it includes information about all, not just insertions on the boundary, but also arbitrary times.
It does. Yeah, I mean, again, as before, like because by hand we choose these to be, these are S's describing both boundary propagators. I think I would want to check before saying this whether you would kind of lose some information because you're restricting to really both boundary objects. But you're right, because you have the z, like if you work in Poincare coordinates, you have z to the power of s. And when you do the z integral, you can insert it at a cutoff which is before the boundary, and in principle you would get, this would give you an answer which is in the system which would be at a generic fixed time. And when you go to the boundary, you select a residue of the Mellin integral which gives the leading term, and this limit z0 goes to 0. So in principle, this Mellin representation does encode information about a generic fixed time as well. But I would like to be sure that you don't lose any information in this process.
Okay, thank you.
Okay, yeah, so this is the all I have to say about 3-point contact diagrams. So if you have any more questions about 3-point contact diagrams, you should ask them now. Okay, so now that we've covered 3-point contact diagrams, we can move on to more interesting observables such as...
Sorry, Shal, maybe you said this, but one famous example, in ADS 5 cross S5, there were sort of these extremal correlators where where funny things happen in ADS.
Mm-hmm.
And are your phases going to get rid of that funny thing in that situation, in the analog de Sitter situation?
It could be. You just have to work out whether there's a 0 of this sign function for those values of the thin and scaling dimensions.
Yeah, okay.
I don't exclude that if you. It could also be that you have some funny thing happening in ADS, and this funny thing carries over to de Sitter. Okay. I was just saying that there are examples where, like in ADS, something weird happens, but it seems to be cured in de Sitter space.
Okay, thank you.
Okay, so yeah, as I said a few slides ago, once you have your constituent 3-point contact diagrams, as we will see in the following, this Mellin formalism allows you to implement quite straightforwardly implement the basic criteria that determine or fix the corresponding exchange at tree level. And this works in the same way for both ADS and DS. So let me first explain how this works in anti-de Sitter space, for which we maybe have a little bit more intuition. So as we saw earlier on in the talk, in this Mellin formalism, we can reconstruct an exchange from its on-shell piece by multiplying with this cosecant factor that encodes the contact terms. And this is quite a nice thing because the on-shell object is a much simpler object to deal with and to construct. So this means that in the following, we can just focus on the on-shell exchange, which I always denote by this red cross here on the internal leg. And this is fixed by a combination of factorization, conformal symmetry, and boundary conditions. So by factorization, it's just like in flat space, like due to locality. So we've seen that boundary conditions are quite straightforward to implement in this Mellin formalism. So it just amounted to a projection operation on these internal Mellin variables. So let's first look at the requirement of factorization and conformal symmetry. So for factorization, you can just think about taking the constituent 3-point contact diagrams, which mediate the exchange that you want to compute, and multiply them together. And there's a unique object that you can form that is consistent with conformal symmetry, and it's this guy here on the slide, where where the internal leg of one of the 3-point factors is subject to the delta plus, the Dirichlet boundary condition, and the other is subject to the delta minus boundary condition, the Neumann boundary condition. So this object in conformal field theory is often referred to as a conformal partial wave. It has some nice properties. In particular, it's a single-valued eigenfunction of the conformal Casimirs. And in this setting, in order to be consistent with factorization, this conformal partial wave is normalized so that it's consistent with factorization in anti-de Sitter space. So these are literally the 3-point contact diagrams in ADS. So this object is consistent with factorization and conformal symmetry. It describes the on-shell exchange of a particle in ADS with a boundary condition that is fixed by the definition of the conformal partial wave itself. This is symmetric if you replace delta plus, invert delta plus and delta minus. So it's some linear combination of Dirichlet and Neumann boundary conditions. So to access more general boundary condition, the key thing to note is that this conformal partial wave is the boundary counterpart of the harmonic function in the book, which we were using earlier on to construct our propagators. So in particular, the quadratic Casimir equation that is satisfied by the conformal partial wave is equivalent to the source-free equation of motion satisfied by the harmonic function. And this duality is made manifest by what is known as the split representation of harmonic functions. So you can express them as a product of two bulk boundary propagators, where one of them is subject to the delta plus boundary condition and the other is subject to the delta minus boundary condition. So you can go from the harmonic function to the conformal partial wave and back by just attaching or removing these external legs. So this means that to implement a given boundary condition on our exchange field in the exchange, you simply have to multiply this conformal partial wave by the precise linear combination of the projectors omega d and omega n that implement that boundary condition at the level of the on-shell propagator, like we saw earlier on in the talk. So is this step, are there any questions at this point? So, so this is the final form for the on-shell exchange, which we fix by a combination of factorization, conformal symmetry.
Sorry, you said this before, but can you tell us again what these projectors are, please?
So they are
so they project Dirichlet boundary conditions and Neumann boundary conditions at the boundary. Yes.
Yes. So maybe it is more clear in a few slides. But so yeah, this harmonic function, because it's symmetric in delta plus, replacing delta plus, switching delta plus and delta minus, it means that it has both of these modes on the boundary.
Yes.
And the Dirichlet, these projectors, these modes are generated by certain poles in U and U bar in the Mellin representation of this harmonic function. And these projectors, omega d and omega n, they have some zeros which are carefully tuned so that they project out the modes that violate the boundary condition that you want to implement.
Okay. Yes. Thank you. So choosing, let's say, beta equals 0, or maybe alpha equals 0, one of the two would give you standard kind of correlators.
Yes, yes. So beta equals 0 will give you the usual Dirichlet propagator Dirichlet boundary condition.
Thank you.
Yeah. So yeah, this is the final form for the on-shell exchange, which we fix by a combination of factorization, conformal symmetry, and boundary conditions. And these are quite straightforward to implement in this framework. So it just amounted to gluing together these basic building blocks in a consistent fashion. And the final step, so to get the full exchange from its on-shell piece, is to multiply by this cosecant factor that encodes the contact terms. And as we will see in a few slides, essentially the poles in U and U bar that are carried by this cosecant factor, they generate the effective field theory part of the exchange from its on-shell piece. And the nice thing is that, notice that in obtaining this expression, we didn't have to evaluate any complicated bulk integrals. So we essentially bootstrapped this full expression for the exchange from the knowledge of these known constituent 3-point contact diagrams. So given the similarities between boundary correlators in ADS and DS that are in some ways made manifest by this framework, and each of the steps that we've just taken to determine the ADS exchange can be carried over to de Sitter. So in de Sitter, as we've seen, the exchange decomposes into the various possible contributions within the in-in formalism. And there are 4 of these in total, which is represented by this sum here, because the 2 points in the bulk can each sit either on the plus or minus branch of the in-in contour. And each of these contributions in this sum is fixed precisely how we fix the ADS, the on-shell, which is this cross here. Each of these contributions in this sum is fixed just like how we fix the on-shell exchange in ADS. So individually, they're each fixed by a combination of factorization, conformal symmetry, and boundary conditions. So for factorization, so focusing on a given contribution in this sum, for factorization, you would take the constituent 3-point contact diagrams from the appropriate branches of the in-in contour. So where one point is on the plus or minus branch and the other is on branch, which I call plus or minus hat. And you multiply them together. And again, the unique object that you can form that is consistent with conformal symmetry is the conformal partial wave. This object here is in fact proportional to the conformal partial wave that we saw in ADS, which is perhaps most straightforward to understand from what we saw earlier, where 3-point contact diagrams in ADS and DS differ by a constant. So this...
I'm very sorry to constantly interrupt.
It's great.
Yes.
I feel less alone in this way, it's great.
Okay. I understood that you managed to compute exchange diagrams in ADS in this very, very clever way. Mm-hmm. But now a 4-point function could, in addition to exchange contributions, have a contribution from just a bulk contact term.
Yes.
And that's not just completely determined by 3-point exchanges, right? I mean, there's some additional data in that. Mm-hmm. Where did that go in your way of thinking?
So yeah, maybe this is a technical point. So so first of all, in obtaining we start with the on-shell exchange, and so we kind of throw away these contact terms, right? We forget about them. So we're solving like the Casimir equation, which gives you the contribution from the on-shell physical exchange single particle state. Now to get the full exchange, we then multiply by this cosecant factor, and there's an ambiguity, like which contact term does my exchange contain? So this is encoded. Okay, so in this Mellin formalism, you represent a function by gamma functions. And this cosecant factor, you can express, there's these identities that express a cosecant factor by a product of two gamma functions, I think, yeah. And you get different answers for your Mellin representation depending where you choose the integration contour. And there's an ambiguity in the way that you can split this cosecant factor in terms of gamma functions, and this selects you different integration contours in your Mellin integral. And these different choices of integration contours that are available in these identities for the cosecant factor, these parameterize the ambiguity in adding contact terms in your exchange. Okay. This is a bit technical, so I don't know if I explained it in a clear way.
Okay, and there should be an infinite amount of ambiguity.
Yes, precisely because the integration contour is select, so because you have your gamma functions and you choose the integration contour such that you separate poles that go off to plus infinity and go off to minus infinity. And these there are infinitely many ways in which you can express this cosecant factor as a product of gamma functions with poles going off to plus and minus infinity.
Right. In fact, there should be a two-parameter infinity because you should have a function of S and T.
That's yes, I don't know how you would see that, but it must. So what we did at least check is that these different ways of splitting the cosecant factor, they accommodate for the entire basis possible quartic interactions that you can supplement your exchange with. So we could generate any contact term that we wanted through this splitting.
Okay, great. And by doing this, by writing down the cosecant, you've chosen just one choice. Is this right?
It might seem. At this level, I haven't specified how I split my cosecant factor. In principle, at this level, it's just a generic choice of contact term.
Okay, thank you.
That was a great question. Not everyone asked that question.
Sorry, I have a question. Yes. So let's say if I am focusing on a particular 4-point function, let's say I'm interested in computing scalar 4-point function. Mm-hmm. And I'm also interested in I have a vertex which is scalar graviton. So mm-hmm. Basically I'm looking at scalar 4-point function by a graviton exchange.
Yes.
So for that contact term factor that you are multiplicating, so in that case I must also know what is a scalar 4-point vertex in the bulk.
Yes.
But if my theory doesn't have that vertex, let's say, to start with, I have just an interaction in an effective theory. I have a scalar graviton 3-point function in the effective theory in the bulk. And I can very well calculate maybe whatever complicated way of computing a Wheaton diagram, a scalar 4-point function with a graviton exchange. Mm-hmm. But then I need to know, because of this contact term factor that you are, cosecant factor that you are multiplicating, what is a scalar 4-point function in the bulk? Is that a correct way of thinking, or I'm missing something?
I'm not sure I fully understand the question. So, because when you have an action, if I understood, correct me if I missed. Because you like the kind of the off-shell terms in the cubic vertex in some way talk to the quartic vertices, right? So on the one hand, you can choose your cubic vertex and put some of your quartic interactions in your contact terms in your quartic vertex, and you would compute the exchange from that known 3-point vertex. And then of course, like that's not the full amplitude in your theory, and you'd have to supplement it by the corresponding contact diagram generated by the quartic vertex that that you've ignored so far. You can also choose to put all of this contact terms within the off-shell terms in your vertex as well.
I see. Okay.
Does that answer your question? Or?
Yeah. Okay.
Okay. Which slide was I on? I forgot now. I was here, right? Yeah. Yes. So we were focusing on a given contribution within the formalism, and we're fixing the on-shell part with each contribution. And for factorization, you take the 3-point diagrams from the appropriate branches of the in contour. And again, the unique object that you can form that is consistent with conformal symmetry is the conformal partial wave. And this has to be proportional to the conformal partial wave that we saw in ADS, because we know that 3-point contact diagrams in ADS and DS just differ by a constant. So this conformal partial wave here is now normalized so that it's consistent with factorization in de Sitter as opposed to factorization in ADS. And at this level, you can effortlessly pass between ADS and DS. So for instance, you can start from the conformal partial wave that we saw in anti-zeta space, and you multiply each leg by the phase that implements the Wick rotation to the appropriate branch of the in contour in the zeta. So at this point, we can just continue like we did in anti-zeta space. So to implement a given late time behavior of the exchange field, you again multiply the conformal partial wave for each in contribution by the appropriate linear combination of these projectors omega d and omega n that implement that boundary behavior at the level of the corresponding propagator. So this is just like we did in anti-zeta space. And to get the full contribution to the to the on-shell exchange in the zeta, you have to sum the contributions from each branch of the in contour. And again, if you want the on-shell exchange in the Bunch-Davies vacuum, you make this choice for the coefficients alpha and beta. So just like in ADS, this is how we fixed the on-shell exchange in the zeta. And again, the final step is to reconstruct the full exchange from its on-shell piece. You multiply by this cosecant factor that contains the contact terms. Is there any questions at this point? So now I'll move on to something else.
Sorry, a possibly vague question. You explained how there was this contact term ambiguity in your 4-point function. Is there a way of fixing that ambiguity so as to get slowest Rege growth, so that the 4-point function grows as slowly as possible in the Rege limit?
In principle, yeah, of course you could do that. I haven't tried, but yeah, of course
it would be possible to implement that. So
yes,
that
yes.
would give us a canonical.
Yes. The choice that we always worked with, there was for no particular reason, was just the simplest splitting of this cosec. So like where you would have, what is it? This is whether the identity where it's like gamma z, gamma 1 minus z. This seemed to give the simplest form of the contact term, but of course there are other requirements that you can fix. You can also fix such that you get like various soft limits of your exchange and so on. There are various things that you can implement that would fix this contact time ambiguity.
Okay. Thank you. And Sophie, you've been describing scalars, but you could do all this for spinning external particles as well?
Yes. So here, I mean, it's completely general framework. So this 3-point contact diagrams are also for spinning fields as well. Generic triplet of spinning fields.
Thank you.
These factors, these alpha and beta factors, does it depend on whether the spinning fields are bosons or fermions?
It could, yeah. I mean, at this level they're generic, but of course, like if you're making a specific choice of the alpha vacua, then this would differ. These factors might well differ depending whether you're dealing with bosons or fermions. But we haven't looked at fermions, so I'm not sure what is the concrete answer to this question. In principle, yes. Okay.
Sorry, Charlotte, I wasn't going to ask you, but now that you bring it up, I mean, the natural connection is, of course, between the Bunch-Davies and the Euclidean ADS vacuum. Mm-hmm. But if you go to alpha vacua, what do you have to do? I mean, are these phase factors? Can you still get away with just phase factors, or do you have to work harder? I mean, it's a much more complicated connection, or not?
So one way to do it is, so we establish these alphas and betas by taking the known propagators and rewriting them in this Mellin form and then reading off what are these coefficients alpha and beta. The other alpha vacua, we know that you can express 2-point functions in alpha vacua in terms of the 2-point functions in the Bunch-Davies vacua, and they differ by phases that depend on this alpha parameter. So again, you would have, if I remember correctly, you would still have like this form here, but you would have like additional exponentials of alpha and some other stuff. So it's not, you'd have to do a little bit of work, but it's not hard. It's just technical.
Yeah. Okay. Thank you. Thank you.
Okay. So before moving on to explore what we can uncover from exchanges in the zeta using this framework, let's briefly pause to understand what we can already uncover from the steps that we've just taken. So in particular, given that the basic criteria we use to determine these exchanges are universal to both ADS and DS, so it was simply factorization, conformal symmetry, and boundary conditions, this tells you that a given exchange in de sitter, so for a given choice of early time vacuum, can be expressed in terms of the corresponding exchange in anti-de sitter space, so generated by the same cubic vertices, and with a specific linear combination of Dirichlet and Neumann boundary conditions, together with some factors that accommodate for the change in three-point function or OPE coefficient as you move from ADS to DS. This ensures that the requirement of factorization continues to be fulfilled. And given the universal form that we've seen that exchanges both in ADS and DS take within this framework, the precise linear combination of Dirichlet and Neumann ADS exchanges that appear in the given de sitter exchange can be straightforwardly determined using the relation that we saw a few slides ago between three-point contact diagrams in these two spacetimes. So in particular, a few slides ago, we saw that the contribution from a given branch of the in-in contour to a de sitter three-point contact diagram is given by its ADS counterpart multiplied by a constant phase. So if we apply this relation to each in-in contribution to the de sitter exchange, this immediately re-expresses it as a linear combination of Dirichlet and Neumann exchanges in anti-de sitter space. So for instance, to get this term here involving the exchange with Dirichlet boundary condition, you would apply this relation to our expression de sitter exchange, and you would collect together the contributions from each combination of branch of the in-in contour involving this projector omega d, which projects onto the Dirichlet boundary condition. So collecting those terms together gives you this term involving the exchange in ADS with Dirichlet boundary condition that you see here. And similarly for the exchange, the contribution from the ADS exchange with Neumann boundary condition, you would again use this relation for each term within the in-in formalism, and you would focus on the contributions that involve this projector omega n. So in this way, you obtain this decomposition of the de sitter exchange in terms of a linear combination of these ADS exchanges with Dirichlet and Neumann boundary conditions. So you should recognize this product of sign factors as the factors that as the sign factors that we saw earlier on. So these are the sinusoidal interference factors that multiply a three-point contact diagram in anti-de sitter space to give the corresponding full three-point contact diagram in de sitter. So these sinusoidal factors here are what precisely accommodate for the change in three-point function or OPE coefficient as you move from ADS to DS. And the factors that remain, so this alpha plus and alpha minus, these are what parameterize the dependence of this decomposition on the choice of vacuum at early times in de sitter. So for the Bunch-Davis vacuum, this would correspond to this choice of this expression for alpha plus and minus here on the bottom of the slide. So you obtain this by simply applying this procedure that I just described for these coefficients alpha plus alpha and beta here on the previous slide to get this decomposition. Are there any questions about this this point? Okay. So this expression is exciting because it tells you that although we established this expression using the Mellin-Barnes representation in momentum space, this relation between exchanges in de sitter and ADS, it holds regardless of the way that we choose to represent these exchanges. So it holds both in position space and momentum space. So this relation provides us with a way to try to import the techniques and results that have been so useful to help us understand the properties of exchanges in anti-de sitter space to try to gain a similar level of understanding for exchanges in de sitter. So in our paper that appeared a couple of weeks ago, we started to make some initial steps to explore the consequences of this relation. And the most straightforward thing that we could do is, for instance, define tree-level Mellin amplitudes for exchanges in de sitter. And this relation tells you that the Mellin amplitude for an exchange in de sitter is given by the sum of the Mellin amplitudes of the Dirichlet and Neumann exchanges in anti-de sitter space. We could also explore the behavior of the exchange in de sitter under crossing, which this relation tells you is inherited immediately from the known crossing decompositions of ADS exchanges. So these are just some very preliminary steps towards efforts to extend the reach of the Conformal Bootstrap program to the Euclidean Conformal Field Theory's dual to physics in de sitter space. Any questions at this point? So
Hello?
It would also be...
Sorry. Yeah, so at this point, can I replace the right-hand side, the anti-de Sitter, by just a general conformal field theory? Would it still give a sensible answer? Like a Euclidean...
You mean the general CFT correlator?
Yeah. Can I just... Would that still satisfy all the properties that you had said about factorization and so on and so forth?
So this holds at any, so I mean, at the 4-point level, there are two types of solutions to the conformal water densities, right? There's just the exchange, and then there's the contact diagram. And this relation here is holding for the solutions to the conformal water densities that corresponds to exchanges in the bulk.
Yeah, so no, I was just asking that, you know, like, does this statement give something about how de Sitter expressions can be written in terms of some Euclidean conformal field theory correlators? Like, does that help you? Since you've related the de Sitter to the anti-de Sitter, Euclidean anti-de Sitter answer, and we know already the Euclidean anti-de Sitter answer is like a conformal field theory answer. So can I also interpret this as just saying that de Sitter is these sign factors into some conformal field theory answer? Can I just feed any conformal field theory answer, Euclidean conformal field theory answer, into this expression?
You mean from ADS?
It is physically consistent.
Yeah, I mean, this relation is allowing you to import anything that you've, like, about exchanges that you've computed in ADS to de Sitter. So you can, for instance, you can, as I said, you can use this to find the crossing decomposition of exchanges in de Sitter, which is inherited from those anti-de Sitter space. You can even try to apply techniques like an inversion formula that have been developed purely in the context of ADS also to de Sitter. It's, yeah, it holds regardless of the way that you choose to represent these exchanges.
Charlotte, I mean, so far your presentation has talked, you have talked about exchange diagrams specifically, right? But I think Laura's question was more general about correlators, which would involve...
Okay, sorry. Yeah, so this is...
Yeah, I mean, this could be perturbative, non-perturbative, you know, higher order.
Really, yeah, this is purely perturbative. So this is purely for tree-level diagrams. But you can, and as we're doing at the moment, you can derive similar expressions, for instance, for loop diagrams. So you can express, for instance, the Candy diagram in de Sitter in terms of a finite sum of Candy diagrams in ADS dressed with appropriate sign factors.
But more generally, aren't these sign factors coming from some sort of a discontinuity, you know, some way of analytic continuation? So in that sense, any correlator, you could say that you would compute some sort of a double discontinuity or something, and then add them up in order to produce analogous de Sitter expression, which in the exchange case would reduce to this prescription, but also be valid more generally.
Yeah, this is precisely the point. Yeah, this would be the general prescription to derive such relations, also potentially at the non-perturbative level as well. But yeah, what I did so far was purely perturbative at the level of the exchange. But yeah, that's a good point.
Sorry, just related, the Dirichlet 4-point function in ADS corresponds to 4 operators of dimension, let's say delta, whereas the Neumann prescription would correspond to insertions of operators of dimension d minus delta. Is this right?
Yes.
So it would be a linear combination of 2 different kinds of correlators of operators of different dimensions.
Yeah, for the exchange field, yes. But I kept the external dimensions fixed.
Oh, so I see. It's only the exchange that is Dirichlet and Neumann. The external dimensions are wherever they are. Okay.
Yeah.
No, but in a non-perturbative case, then how would you say this? Because when the composition in terms of exchanges may not be most natural in that case. Some description purely in terms of what you do to the external guys would be more natural. So in that case, is there a way to impose these boundary conditions? Sorry, maybe this is, don't know whether it's a well-posed question, but I'm just saying that when you don't quite have an interpretation in terms of exchanges, how is it that I should impose various boundary conditions? Because those should make sense even non-perturbative.
Yeah, that's true. Yeah, this I haven't thought about much at all. Yeah.
Maybe I'm not sure, but maybe there is a corresponding statement in terms of just the like a conformal block and a shadow conformal block. Isn't that the kind of the spirit of this addition, that that there is some answer that you want to get, and you're using a conformal block plus a shadow conformal block, which is this d minus delta exchange.
Yeah, right. Yeah.
I mean, so there's some combination which gives you the answer. That if stated that way in the expansion, it's non-perturbative.
Maybe.
I mean, one way that one might try to think about non-perturbative is kind of in the context of like this Polyakov-Mellin bootstrap, you know, where it's natural to decompose in terms of exchanges as a basis to organize your 4-point correlators. But yeah, a lot of these questions about the non-perturbative nature of correlators in situ is not so clear to me, because it's, for instance, can we assume things like convergence of the OPE, which a lot of these properties, at least the ones that we've established in ADS, they seem to rely on this this property. So I'm always a bit hesitant to extend intuition from ADS.
Also, the single trace and double trace exchanges seem to be in slightly different footings here, in the sense that roughly what you're dealing with is the single trace exchange. Then the various contact diagrams talk about the double trace exchanges, and those are not being dealt with in the same way.
Yeah. I mean, one way that you could try to incorporate them is purely within the cubic vertices of your exchange diagrams. But maybe it's a bit unnatural. Yeah, these things I haven't really thought about so much. No, thanks.
Sorry, I have a question. Sorry. So this, it's probably related to the question that Loga was asking. So still now we're like representing relations of bulk diagrams, exchange diagrams between ADS and de-Sitter. But if I now focus on the ADS exchange diagram, there is a bulk integral, right, on the vertex in the bulk, if I just want to compute it. Now there is a situation where there are things like geodesic Witten diagrams, where you don't need to do the full bulk integral, but you just place it on the geodesic of the that connects the boundary points, and that is kind of known to be dual to the conformal blocks in the CFT. So is it possible to in that sense relate to some CFT stuff, which is the conformal blocks, and probably, I mean, without doing the bulk integral on the right hand side of your equation, and thinking it in terms of some geodesic Witten diagram?
So you mean you want to replace the exchanges that you see here with geodesic Witten diagrams?
I mean, this is a equivalent way of computing the exchange diagram in the ADS, where you don't need to do the bulk integral over the whole bulk of the vertex that you insert in the bulk, but just place it on the geodesic that connects the two external points. And they are thought to be dual to the conformal blocks in the dual CFT in the ADS picture. So in that sense, maybe there is a connection with direct CFT objects like conformal blocks with the de-Sitter exchange diagram. I don't know.
Yeah, I mean, certainly. Yeah, I mean, yeah, this is one way to think about it, because I think also for geodesic diagrams, I mean, this relation would hold, because the geodesic, so yeah, the conformal block, for instance, would correspond to, yeah, it's precisely this guy here, but you put this internal leg on shell, so you would have a cross here. So I mean, yeah, these relations would. So what you're saying is that potentially by replacing these exchanges with geodesic diagrams, perhaps this is a more natural way to restrict to like concrete CFT objects, as opposed to, yeah, perturbative objects in ADS.
Yeah, thank you.
Okay, so yeah, for me it would also be interesting to understand like how this Mellin-Barnes representation in momentum space could even be put to use within the context of the conformal bootstrap. So in the following, I will explain how we can use this, so returning back to this full Mellin-Barnes representation of exchanges in momentum space, we'll explore a little bit what we can uncover about exchanges and interactions in the city using this framework. And so in the following, I will focus, for concreteness, I will focus purely on exchanges in the Bunch-Davis vacuum, which corresponds to these choices for the coefficients alpha and beta. Okay, so the imprints of particle, like of a physical exchange particle, these are particularly so the signal that would distinguish it from a local quartic contact interaction. And this is particularly sharp in the limit where the exchange momentum Ki is soft, which in position space on the boundary corresponds to taking these two pairs of points to be far apart. So the behavior of your 4-point function in this regime is a good diagnostic of whether or not a particle or particles have been exchanged between these two pairs of points. So this limit has been explored of exchanges in de Sitter and also in ADS have been explored in numerous works. Our analysis is most similar in spirit to that of Akane and collaborators who also used conformal symmetry and general consistency to classify such signatures at tree level for external conformally coupled and massless scalars in D=3. And using the Mellin formalism, we could extend their results to a generic collection of particles and general bounded dimensions D.
Sorry, Charlotte, could I ask, just in Euclidean CFT, is there a precise sense in which in the limit that you talked about, these Ki's much, much less than Kj's, there's an operator product expansion of correlators in momentum space?
I mean, I think the OPE is always, there's always a sense of operator product expansion. I think for me, as far as I understand, the question is whether, so in ADS with an important property which allowed us to, which many techniques in the Conformal Bootstrap rely on, is the fact that this OPE is convergent. In the system, maybe it is, but for me, it's not established whether you can take this for granted in Euclidean CFTs. So in order to import many of these ADS techniques to de Sitter, this fact should be established. But the OPE in general, this limit and so on, is I think it makes sense to talk about it.
I'll just re-ask. In position space, it's clear there's an OPE. You bring two operators.
Ah, you mean in momentum space?
Yes. Since you're integrating over all positions at any momentum, it wasn't totally clear to me that an OPE ever makes sense.
I see.
Do you know if there's a clean statement about OPEs in momentum space?
No, especially in Euclidean CFTs, no. I think in normal Lorentzian CFTs, yeah, this is I think this is understood. But Euclidean CFTs, no, I have nothing to say about that actually.
Where is it understood in Lorentzian CFTs?
I think there's been some recent papers by, I think João Penadones and also Helios.
Okay, thank you. Thank you.
But yeah, Euclidean CFTs, I don't know about this actually.
Shiraz, I'll have to go back and look, but I do recall when we did our work, for example, on 3-point functions and so on, some of that was also with Suvrat. I'll have to check, but I think by Fourier transforming suitably the position space correlators, sometimes I think you can make statements, at least about the behavior which would follow from OPEs. But I'll have to go and look. But it's not entirely impossible, right? I mean,
it's not impossible, but at least in one project, I've run across a situation where terms that you would ignore because of the Fourier transform start becoming dominant. So it's not impossible, but I don't think it's totally automatic. In fact, there was a paper by Komargodsky in which he discussed, he talked about how there were various subtleties in momentum space OPEs and basically said that he thought it didn't make sense.
Really?
4 or 5 years ago, but that's a long time ago. That might have been progressing.
No, I don't know. I see. Okay. Okay. Yeah, but I do recall that because we had used, typically in this cosmological context, you solve the word identities in momentum space. That's more convenient. And in fact, it sometimes totally fixes things, like 3-point functions as you'd expect. And but with ambiguities, which I think we had to take some OPE analog to fix. It's been a while, but at least there are some analogous constraints I remember in momentum space also. But I can try to look that up. Yeah, it's
the kind of thing that happens is that when you're trying to treat 2 points together as a single effective operator,
yeah,
and that gives you a divergence when you integrate near that operator. The fact that they're actually 2 points smears that divergence out. And then it's a bit hard to capture that systematically. But sorry, please go. I don't know. We can discuss.
Okay. Okay. Maybe. Yeah. I see.
Okay. So can I continue? Yeah. Yeah. So in this Mellin formalism, the Mellin-Barnes representation is quite a useful tool to explore these type of soft limits in any of the momenta. And for the soft limit of the where the expansion of your 4-point correlator in these limits is generated by the residues of poles of the corresponding Mellin variable. So for the expansion of your 4-point correlator in this soft limit of the internal momentum, this is generated by the residues of poles in the internal Mellin variables u and u bar. And you can see this by recalling the way in which the internal momentum enters this Mellin-Barnes representation. So we have an exponent that depends on the sum of these internal Mellin variables, u and u bar. So the residues of these poles generate power law-like terms in the exchange momentum. So for the on-shell exchange, which we know is the piece which should encode information about the physical exchange single particle state, the only source of poles in u and u bar comes from the constituent 3-point contact diagrams, because these projectors omega d and omega n, they don't contribute any pole to this Mellin representation. And these poles in u and u bar, they come from like the internal legs in each 3-point contact diagram. So this leftmost contact diagram introduces poles from the Mellin variable u, and this rightmost contact diagram introduces poles from the Mellin variable u bar. And these are the same poles that we saw earlier on, because they're poles associated to external legs in your 3-point function. And they're in the same location for both u and u bar, and I've plotted them here on the bottom left. So they are integer space, they're 2 infinite families, and they head off to minus infinity. And their location, as before, depends on the mass of the exchange particle, which enters in the usual way through the scaling dimension. So that is somewhat similar in spirit to exchanges in flat space. So where the contribution from the physical exchange single particle state is generated by the residue of a simple pole whose location depends on the mass of the exchange particle. So when the exchange momentum Ki is soft, you can close this integration contour here to the left, and this indeed encompasses both infinite families of poles. So the residues indeed generate the expansion of the on-shell exchange in this soft limit. So on the slide here, you can see the schematic form of this expansion, where I focused first on the case where all of the fields in the exchange are scalars, where each family of poles in u and u bar turns out to generate a family of non-analytic terms in the exchange momentum. So you can understand this by looking again at the way in which the exchange momentum enters a Mellin representation through an exponent that depends on the sum of these internal Mellin variables. So this tells you that the residues of poles here in the upper half plane generates this family of non-analytic terms here on the second line, while the residues of poles in the lower half plane generate the family of non-analytic terms here on the first line. So where the poles which are furthest to the right, these generate the leading contribution in each non-analytic families, and the poles to the left generate like the sub-leading terms. So these non-analytic terms are what are the characteristic signal of a particle exchange. So they can't be emulated by a local quartic contact interaction, where you see that the exponent of the exchange momentum depends on the boundary behaviors delta plus and delta minus of the exchanged field. And on the boundary, this corresponds to the scaling dimension of the corresponding exchanged operators. The fact that you get contributions from both non-analytic families is a consequence of our choice of Bunch-Davis vacuum, so where both of these modes reach the boundary at future infinity. On a practical level, in our expression, in our Mellin representation for the exchange, this arises because the coefficients of the projectors omega d and omega n, they are both non-zero. So if instead, for instance, only the coefficient of omega d is non-zero, then this family of non-analytic terms here on the second line would be absent, because as you see, the poles that generate them have been cancelled by the zeros of this projector omega d, which are these denoted by these yellow crosses here. So this scenario is like more physically meaningful, of course, in anti-de Sitter space, where it corresponds to implementing the Dirichlet boundary condition. And similar applies to the Neumann boundary condition. So if only the coefficient of omega n is non-zero, then the family of non-analytic terms here on the first line is absent, because the poles that generate them have been cancelled by the zeros of this projector omega n. Is this clear? So if the exchange particle instead has positive integer spin, there's also an angular dependence. So here I'm also taking the external scalars, the external fields to also be only scalars. And in general bounded dimensions D, this angular dependence is given by a Gegenbauer polynomial, where the degree of this polynomial encodes information about the spin J of the exchanged particle. So this angular dependence on a practical level arises in our Mellin representation because when your fields have spin, the constituent 3-point contact diagrams now have a tensorial structure which is being contracted together. And when the external fields are all scalars, these tensorial structures encoded in the 3-point contact diagrams, they have been contracted to form a scalar object. And so this introduces a dependence on this angle theta here. If you also have, if your external fields also have spin, then there's also a tensorial structure in this expansion of the exchange in the soft limit. And from our expression for the exchange, you see that this is inherited from the tensorial structure of the constituent 3-point contact diagrams. This can be worked out systematically by working out the contraction of the known tensorial structures of your constituent 3-point contact diagrams. So if the scaling dimensions delta plus and delta minus are real, this expression tells you that that in this soft limit, a single particle exchange is characterized by specific power law behavior in the exchange momentum. So if we're in ADS, this covers all unitary representations of the isometry group, which necessarily have real scaling dimensions. But in the city, you can also have unitary representations that have complex scaling dimensions. And these are in particular the principal series representations where these scaling dimensions, delta plus or minus, have the form shown here on the slide. So they take the form d over 2 plus or minus I mu, where mu is a real parameter. So these correspond to massive particles of massive order of the Hubble scale or higher. So they include precisely the type of particles that can be created by the inflationary expansion. And these particles, they have a rather distinct signature in this soft limit, and this is precisely due to the fact that these scaling dimensions are complex. So they generate an oscillatory behavior as a function of the log of the exchange momentum. So you get this behavior here by taking the leading term in each non-analytic family and exponentiating. And when you sum the leading terms from each family, you get this sine function here. And an interesting observation, which was also made, in these papers here, is that the frequency and the phase delta of these oscillations depend on the parameter mu, which labels the principal series representation. And from this expression, you can in particular show that the phase of these oscillations can be traced back to these sinusoidal interference factors that come from the constituent 3-point contact diagrams, like we saw. So this tells you that the phase of these oscillations in the signal of the exchange of a massive particle, it's fixed by the cubic couplings through which your massive particle decays off into lighter species. So far I focused on the on-shell exchange. In the full exchange, another source of poles in U and U bar comes from the cosecant factor that encodes the contact terms. So these are the red dots here. And consistent with the fact that these cosecant factor encodes contact terms, the residues of these poles only generate terms that are analytic in the exchange momentum. So in particular, the residue of the end pole, which lies to the left of the integration contour, this generates a term proportional to the end power of the exchange momentum squared, which is of course analytic. And the coefficients of these terms is given by the Mellin integrals, the remaining Mellin integrals that are left once you evaluated this residue. So this infinite power series of terms are what, as you start to move away from this soft limit, they start to dominate over the oscillations that signal that a particle has been exchanged. This is somewhat similar to, in spirit, to resonances that appear in particle colliders, which signal particle creation. Yeah, so in certain cases, these coefficients of these terms, they're rather simple. So if your external fields are conformally coupled scalars, these coefficients take this form shown here on the slide, which you get by just evaluating the Mellin integrals in the case where you have external conformally coupled scalars. And the precise form of these coefficients is not so important, but what you should note is the dependence on the mass of the exchange particle, which enters through this parameter mu. And this tells you that these coefficients emit an expansion in the inverse mass of the exchange particle. So this tells you that these terms that are generated by the poles in this co-escape factor, they are what constitute the effective field theory part of the exchange, where the non-perturbative corrections are given by the non-analytic contributions, which are generated by the on-shell part of the exchange. When did I start, actually? How much time do I have left? I started at...
How much time do you think you would need?
I have 14 slides left. I can. How much time do you?
I don't know. 10-15 minutes.
Yeah, I can. Yeah, I can do this. Okay. Let me see. Should I skip? Okay, let me go through this. Okay, so yeah, so let me emphasize that for fields of generic mass and spin, this Mellin-Barnes representation is what captures the full analytic structure of the boundary correlator as a function of complex momenta. So in particular, what I mean is that for generic scaling dimensions, we know that conformal correlation functions in momentum space are necessarily given by these like horrible generalized hypergeometric functions of multiple variables. This is some fact that you have to cope with if you want to study these objects at all. But what you can do is you can look for useful ways to represent your hypergeometric functions. And our perspective is that this Mellin representation is what, for instance, provides the analytic continuation of the hypergeometric series to the entire complex plane, which is cut along the positive real axis. So on the slide here, I just reminded you of the Mellin representation of the simplest type of hypergeometric function, so the 2f1. So in this Mellin representation has been useful to establish identities, transformation formulas, asymptotic expansion, and regularization of singularities, all of which are beautifully detailed in this book here. And you can apply the same methods to the Mellin representation of your boundary correlator. And just like how the hypergeometric series can be recovered from its Mellin representation by evaluating, by applying the residue theorem. So here you would evaluate the residues of these yellow poles here along the positive real axis. And you can also get an expression for our exchanges as an infinite series expansion in multiple ratios of the momenta by applying the residue theorem to each Mellin integral. The expression that you get in the end would only be valid for a certain range of parameters. So it's the Mellin representation that provides a more complete description.
Hello?
Yes?
Excuse me, I wanted to ask a question.
Yeah.
In the beginning of the slide, you showed that the dilatation word identity, they simplify in the Mellin variables. It just becomes S1, S2, S3 equal to constant.
Yes.
Does something similar happen to the, let's say the special conformal word identity?
I haven't explored how the special conformal word identity appears in this Mellin representation because it's kind of taken into account in the exchange, for instance, from these already from the 3-point factors here.
Oh.
Yeah, so essentially you can translate the conformal word identities into like the location, so the conformal word identities in total. So the dilatation word identity fixes this constraint on the external Mellin variables. And the remaining word identities, they fix the location of the poles in the Mellin representation of your correlator. And these are precisely encoded for the exchange in these 3-point factors here.
Oh, okay, thank you.
So for certain values of the parameters, of course, we know that hypergeometric functions reduce to simpler objects that don't require Mellin integrals to be described completely. So for instance, this happens in this identity here, so where the arguments C and B are equal to each other. So the Mellin representation of your hypergeometric function reduces to an object that doesn't need Mellin integrals to describe it at all, so in the entire complex plane. And for Mellin representation for the exchange, this type of mechanism happens like for special representations like massless and partially massless fields. And in these cases, you can completely remove these Mellin integrals in an analogous way to as you see here, which gives you an expression for these exchanges which are completely free from Mellin integrals, so explicitly in terms of the momenta and the polarizations. So on the slide here, you can see the form, that the expression that you get in this way for the exchange of a massless spin J field between two conformally coupled scalars in D equals 3. So you get this expression by taking your 3-point contact diagram involving a massless spin J field and two conformally coupled scalars. You plug it into this expression for the exchange, and then you evaluate the Mellin integrals. So on the slide here, I focused on the contribution from the Elicity J component, because when your exchange field is massless, then this is the only component that encodes information about the propagating degrees of freedom. So the lower helicity components just encode bulk contact terms. So zooming in on this expression, so we have the usual momentum conserving delta function, which we expect. What you don't have is the energy conserving delta function, because this is an observation that is being made at fixed times, so you don't have translation invariance. But what you do have instead is a singularity in the total energy variable ET, which is defined here on the bottom right. So this is the total energy in the high energy limit of the corresponding exchange amplitude in flat space. And in addition to this, you also have poles in the left and right energies E left and E right associated to the left and right cubic vertices. So this is the singularity structure of the exchange. And in the square brackets, what is left is just polynomials in the magnitudes of the momenta. So this is in particular in the square bracket series, a polynomial of degree j-1 in the total energy variable ET. So this expression is a little different from what we're used to from studying scattering amplitudes in flat space. And for comparison, I put the explicit expression for the corresponding exchange amplitude in flat space here on the bottom left. But nonetheless, there are like relics of flat space scattering encoded in our de Sitter correlators. And this statement was made concrete by Maldacena, Pimentel, and Raju, who argued that the residue of the leading singularity in the total energy variable is what gives you back the high energy limit of the corresponding scattering amplitude in flat space, with the total energy conserving delta function stripped off. And the intuition behind this is that that the singularities in total energy, they arise from a region where all of the interactions are taking place at early times. And it's in this region where you can make this high energy in flat space approximation. And this expression here that we get is consistent with their argument, because if you take the ET goes to 0 limit, the leading term comes from the n equals 0 term in this polynomial, which is j-1 powers of the product of left and right energies. And this product of left and right energies gives you the Mandelstam variable S in flat space. And this j-1 powers of S, it cancels with j-1 powers here on the denominator coming from the product of E left and E right. And this gives you the simple pole corresponding to the propagator in the flat space exchange. So in this way, when you take the limit ET goes to 0, you recover precisely the corresponding exchange in flat space. The Mellin integrals can also be lifted in the case where your external fields are also massless. So for instance, this is the expression that you get for the exchange in Yang-Mills theory, again in D equals 3. And
sorry, Charlotte, sorry, please excuse me. If you can just go back to the previous transparency, let me just make sure I understand.
Yes.
What was the variable ET again?
This total, it's this guy here. So if you if you think about it, so here, like, this is the total energy variable in the high energy limit of the exchange amplitude in flat space.
I see. Okay, and I see, sorry. And just so I make sure I understand, because I remember along with Nilay, who's also here in this call, and others, we computed the 4-point amplitude for graviton exchange, which already for us was a pretty ghastly expression in de Sitter. But are you saying the Mellin-Barnes integral is as simple as what you're writing down here? Seems pretty simple to me. Just some polynomials and some poles, that kind of thing. Is it?
So when you mean that, so you mean the graviton exchange between external?
Yeah, for even massless scalars. I mean, it's pretty complicated by the time you put the bulk to boundary and the bulk to bulk, and I don't know. At least I recall it being quite a ghastly experience.
Yeah. So first of all, this is for external conformally coupled scalars, which already has some nice, not simple. But yeah, for the massless, yeah, I mean, it takes a similar form, but it's really ghastly, as you said. I think we even put it in, I think we matched with your expression even in our paper last year.
I see.
But yeah, it's horrible.
I see. But after the Mellin-Barnes, I mean, what I was trying to ask was, do expressions like that, which are otherwise pretty ghastly, do they become much simpler? I mean, is this, or is it just for conformally coupled, etc., scalars that it's
you mean after you evaluate the Mellin integrals, or at the level of the Mellin representation?
At the level of the Mellin representation, before you do the...
Let me remember. There is some simplification, but still, like, so if you write these 3-point contact diagrams in this Mellin form, you still have a similar level of complexity. So like what would be, you essentially, you replace some polynomials in the momenta with a polynomial in these Mellin variables. So it's still like, it is a little bit ghastly.
I see. Okay. All right. Thank you. Thank you.
Okay. Yeah, so this is the expression for the exchange that you get in Yang-Mills theory. On the slide, on this expression here, just to note, I focus on the contribution from the external legs coming from
just a clarification. I'm sorry. But this expression is for exact de Sitter, right?
This expression, yes. Throughout I'm working purely in de Sitter, yes.
Even the previous 4-point scalar exchange with spin J massless, that was for exact de Sitter, right?
Yes.
Not inflation.
No. Okay. But of course, like from this, you could okay, if you you could take you could obtain the leading correction in slow roll to get the inflationary 3-point function from this.
Yeah.
But, yeah, all of this really.
I think that's why it's looking simple.
Right.
Okay. So yeah, so on this expression for the exchange in Yang-Mills theory, I focus on the contribution of the external legs with delta plus boundary condition, because on the boundary, this means that you have these conserved currents J of spin 1. And you obtain this expression in exactly the same way like we did for the exchange of a massless spin J on the previous slide. So you take the 3-point contact diagrams in Yang-Mills theory in this Mellin form, and you plug it into the expression for the exchange, and then you evaluate again the Mellin integrals. The features of exchanges that we saw on the previous slide, they carry over. So you still have your singularity in ET, which you take ET goes to 0 to get the to take the flat limit, and you also have your singularities in the left and right energies, which will give you the simple pole of the propagator in flat space. The new thing, of course, is that you have a tensorial structure, because the external fields now have spin. And so these psi's here are the corresponding polarization vectors. And as I said before, this tensorial structure is inherited from that of the constituent 3-point contact diagrams. So this P plus is the tensorial structure of this leftmost 3-point contact diagram, and this P minus is the tensorial structure from the rightmost 3-point contact diagram. And these are being contracted together, which is why you have a derivative here in the internal polarization psi. And a nice thing to note is that if you look at these 3-point tensorial structures, even at the level of the Mellin representation, and you restrict to the highest listy components, this tensorial structure is quite simple, and it's actually equal to the 3-point Yang-Mills amplitude in flat space. So they have the leading listy component of these tensorial structure takes this form shown here. So this makes manifest that when you take the flat limit, you recover the Yang-Mills exchange amplitude in flat space. So the reason why I mention this example is because it appears again in an interesting way when you consider the exchange in gravity. So gravity is another example where you can lift all of these Mellin integrals. And the nice thing is that precisely due to the double copy structure of scattering amplitudes in flat space, if you look at the tensorial structure, so the contraction of P plus and P minus in your gravity exchange, and you restrict to the highest listy component, this is equal to the square of the highest listy component of the tensorial structure in the exchange in Yang-Mills theory. So this is how the double copy structure of scattering amplitudes in flat space is encoded into the de Sitter correlators. But this structure, let me stress, it only holds at the level of the highest Licity component. So this type of relation gets broken by the lower Licity terms in these tensorial structures, as well as the polynomials that appear in the magnitudes of the momentum. So any questions at this point? Yeah, I had another section of the talk on constraints of massless particles, but maybe I'm free, but if anyone is getting tired, then I can also summarize.
How long is this? How long do you think it would go?
I think I would need like
the next section.
10 minutes.
So maybe we should close the talk now and informally continue with the people who are interested. Okay.
Yeah.
Okay. So let's thank Charlotte for a very nice talk first. Let's unmute and.
Wait. Shouldn't we give Charlotte a chance at least to have a conclusion slides up if she wants to? Sorry. Since
okay, I can.
Sorry, Abhijit, up to you. But at least I think that would be nice if it's okay.
Yeah, I will conclude. Yeah, I will conclude. Okay, so yeah, to finish off anyways, a quick summary slide. Yeah, I mean, there are plenty of future directions to explore, all as part of within this Mellin formalism to construct boundary correlators in this framework using this Mellin representation in momentum space. And you would continue in the same way that I tried to outline in this talk. So you would focus on the onshore part of the boundary correlator, which you can then construct in quite a straightforward way by combining together these basic building blocks in a consistent fashion. The obvious next steps would be to construct higher pointer loops in this framework to see what one could understand. And as you would expect, a nice parallel emerges with like generalized unitarity methods and the Kutkowski rules in flat space. And you can see this from writing down the expression for the Candy diagram in this formalism, which immediately reduces in terms of the constituent tree level 4-point contact diagrams. So this is somewhat similar in spirit to generalized unitarity methods that are already been established in like the context of ADS CFT. A little bit more speculatively, would be curious to understand if any of these techniques could be of use in the context of flat holography, so to construct celestial amplitudes, where it would be tempting to suggest that like conformal symmetry on the celestial sphere would constrain the corresponding exchange to take a similar form, where of course you would replace the 3-point contact diagrams here with like the 3-point amplitudes on the celestial sphere. Another thing that I would like, the final point that I would like to mention in some ways circles back to the first and also to what I was saying earlier on in the talk. So for me, it would just be, so in recent years, exchanges have emerged as like a useful basis to organize your 4-point correlation functions, so like in the context of the Polyakov-Mellin bootstrap. So for me, it would just be interesting to understand like whether any mileage could be gained from using this Mellin-Barnes representation in momentum space. So yeah, I will conclude here, and yeah, thank you so much for your attention.
Okay, thank you, Charlotte. Thank you for a very, very nice talk.
Thank you.
You know, so I would love to hear what Charlotte has to say about the massless particles, but I was just wondering, I don't know what the time constraints everyone else has, but could we just have a little bit of discussion in general on the talk, and then some of us can stay back and hear the massless, or it's up to you all. I don't know what you're all interested in. But Charlotte, you have a bit of time, I gather. I don't know.
Yeah, I have a bit of time. Yeah, I can hang around for a bit.
I don't know, whatever you like, Abhijit, but some of you may be more interested. I'm just wondering in some of these, you know, Kutkowski rules, etc., unitarity methods. I'm not sure what you like. Go ahead as you like.
Yeah, I think we could perhaps have a discussion first and then get to the section that Charlotte wants to cover later.
Okay.
That work? Would that work with you, or would you rather talk about the stuff that you skipped?
No, we can discuss. Yeah, I'm happy to. Yeah, we can discuss, and then if anyone is interested to hear the rest, then I can also go through that afterwards.
Okay.
Sorry,
So,
just before that, like what was the section that you had skipped in one or two sentences? What was the?
So it was studying the essentially like doing some kind of analogous analysis to Weinberg's to doing the analog of Weinberg theorem in de Sitter. So how it appears in this Mellin formalism and how these constraints coming from massless particles manifest themselves.
Oh, okay.
In this way, we could, for instance, show that just like in flat space, there are no consistent interactions of massless higher spin fields to scalars if you insist on local interactions. And in de Sitter, this is nice because you can also use this framework to study constraints on particles that are more inherent to de Sitter, like partially massless and so on. This is why it was interesting for us.
Okay. Yeah. Okay.
Maybe you could even talk about this first, if you rather than we could have a discussion session over all the whole of the talk.
Yeah. Okay. Yeah. If people. If people are interested, then I can. Yeah. I think it will just take like 6 minutes. I think something like this.
Sorry.
Okay. So shall I proceed?
Yes, please.
Okay. Yeah. So moving back to the Mellin representation for the exchange, let me stress that this is valid for, this expression here is valid for a generic collection of internal and external particles. So in deriving this expression, I took these scaling dimensions delta to be generic. But of course, like ultimately, one is interested in unitary representations of the de Sitter isometry group. As we've seen, this expression is valid for special representations like massless and partially massless fields, in the sense that in these cases you have to plug in the corresponding gauge invariant three-point functions into this expression for the exchange, as we just did here for Yang-Mills and gravity. And gauge invariance actually manifests itself in quite an interesting way in this Mellin representation. And a simple example to consider is the cubic coupling of a massless spin J field to two scalars. So where gauge invariance requires that the lower holistic components in the corresponding three-point contact diagram do not contain bulk contact terms. So this means that they are at most boundary terms, and in particular, it means that they shouldn't have a singularity in this total energy variable ET. So such a singularity is the characteristic of a contact term. So for an exchange, you would also have a singularity in the left and right energies, and for a contact diagram, you would purely have a singularity in ET. And gauge invariance requires that in these lower holistic components, such singularities are absent. So how does this requirement manifest itself in the Mellin representation? So we saw that in this Mellin representation, a contact diagram has these Dirac delta functions which are enforcing the constraint coming from the dilatation ward identities. And if you make the listed decomposition of your three-point contact diagram, these Dirac delta functions are present in each helicity component with an argument that is shifted by the number of longitudinal indices, J minus M. So in order for these lower holistic components to be boundary terms, which are required to be consistent with gauge invariance, in each of them, we require that this Dirac delta function is accompanied by a factor that is equal to its argument. So just like how boundary terms emerge in momentum space, like I reviewed here. So in momentum space, if you take a Dirac delta function as a function of momentum and multiply it with, again, the momentum, then you get a boundary term of this type. And the same mechanism is happening here, but for boundary terms in the bulk radial coordinate. So this precise combination, so this factor here multiplied by the Dirac delta function multiplying the Dirac delta function by a factor that is equal to its argument, this precise combination is representing a local boundary term in the Mellin representation, which arises from the integral of the bulk radial coordinate, which for de Sitter is eta, which is the conformal time. So in order for the lower holistic components, so this factor here is that multiplies the Dirac delta function is what is cancelling the bulk contact term that this Dirac delta function encodes. So in order for the lower holistic components to be, so since three-point conformal structures involving two scalar operators and a spinning operator is unique. In order for this 3-point conformal structure to also be consistent with gauge invariance, this kind of structure should appear in the lower holistic components when you take the limit where the spin J field becomes massless. And if you do that, you find that this only happens if the scalars have the same mass. This is consistent with what we already know about the consistent cubic couplings of massless fields to scalars. They can only exist if the scalars have the same mass. And if you continue in this equal mass case, the boundary terms that you get are finite and non-zero, and so they give you a corresponding non-trivial Ward-Takahashi identity. And these Ward-Takahashi identities appear in quite an interesting way in this Mellin representation. So they're generated by a finite number of poles which satisfy this constraint here. So this constraint here, which appears in the exponent of eta naught, which is the regulator in the boundary term, is what is setting to 0 this exponent. So when you take the regulator eta naught goes to 0, this gives you a finite boundary term. And these poles here are the poles associated to the external legs, and a finite number of them are satisfying this constraint. So the lower holistic component that you go, the greater the number of poles that is contributing to these boundary terms. So in this way, for instance, you get this Ward-Takahashi identity for the holisticity J-1 component. This is the simplest type of Ward-Takahashi identity because it's the highest lower holisticity component, so the least number of poles contribute. So the Ward-Takahashi identities for the lower holistic components, you obtain them in the same way, but they are more complicated because more poles satisfy this constraint. So now that you have your gauge invariant 3-point functions, you can then plug them into our, which you know, and so you know these only exist for the case where the scalars have the same mass. You can then plug these expressions into our expression for the exchange. And gauge invariance at quartic order famously constrains the cubic couplings G. So these couplings G were left unscathed by the cubic analysis that we did on the previous slide. And a simple example to consider is the exchange of a scalar generated by our cubic coupling with a single external massless spin J field. And to explore the constraints coming from gauge invariance, you take the full exchange amplitude, so the sum of the S, T, and U channels, and you contract with the boundary momentum K1 associated to the external massless spin J. So you project onto the longitudinal components. So what do you get if you do that? So first of all, you get a term that gives you the right Ward-Takahashi identity. This is in fact inherited from the Ward-Takahashi identity that we saw on the previous slide at the 3-point level, because this is generated by the on-shell exchange, which we know factorizes into these constituent 3-point contact diagrams, one of which is the gauge invariant 3-point function that we just considered. But in addition to this, there are also terms that violate gauge invariance, and these come from the non-factorized part of the exchange. And these terms correspond to bulk contact singularities. So they have singularities in the total energy variable ET at quartic order. So in order to restore gauge invariance, one thing that you can ask is if there exists a local quartic contact interaction, and by local I mean with a finite number of derivatives, that would cancel these bulk contact singularities to help you restore gauge invariance. And so to proceed, you can classify the singularities in ET that can be generated by all possible such local quartic contact interactions. And if you subtract all of them off from the exchange, you still find that left over, there are singularities in ET that are purely exchanged, that can't be generated at all by a local quartic contact interaction. So this is what gives you the constraint on these couplings G, because to achieve gauge invariance, these terms have to then vanish by themselves. So this is analogous to Weinberg's analysis in flat space. And in particular, if you look at the holisticity J-1 component of your exchange, you get a constraint of this type. So where the exponent in ET, so hash here, is just some power that can't be generated by a local quartic contact interaction. And the factor that multiplies it is precisely the factor that comes out of Weinberg's analysis in flat space. So the same conclusions hold in sitter as they do in flat space. So for spin 1 and spin 2, so plugging in J equals 1 and J equals 2, you get charge conservation and the equivalence principle, which was also obtained in a paper of May this year by Daniel Baumann and collaborators. And using our results, we could obtain the higher spin constraint. And the precise statement is that if you insist on theories with local interactions, so with a finite number of derivatives, there can exist no cubic coupling of a massless higher spin fields to scalars, no matter what is the mass of these scalar fields. So since we know that there are theories of interacting massless higher spin fields in ADS and DS, the so-called Vasiliev theories, we have to be careful and state how these theories evade this no-go result. And the point is simply that these theories have non-local interactions. So with they have an action with an unbounded number of derivatives. So the reason for this is because these theories that the spectrum consists of infinite towers of massless higher spin fields with increasing spin. And the interactions of these particles, the number of derivatives increases with the spin. So the Lagrangian has an unbounded number of derivatives. And what you can show is that in order to satisfy the higher spin ward identities, these 4-point contact amplitudes, they have to be as non-local as the exchange amplitudes in these theories. This is precisely how you can restore gauge invariance without having to set these cubic couplings G to 0. And in progress, we're also, so this is the constraint on massless particles in de Sitter, but in progress, we're also working through analogous analysis for partially massless fields. And what we seem to find from our preliminary results is that all of the interactions of partially massless fields to scalars that we've considered are inconsistent. So there can exist so far no cubic coupling of a partially massless particles to two scalars in de Sitter. So yeah, that was the final part of my talk, and yeah, I finished everything that I needed to present.
Okay, great. Thank you so much. I think Abhijit had to run off, so he asked me to just make sure. So, well, thanks a lot, Charlotte, very much. I don't know, does anyone have any questions? Please ask.
Yeah, I had a question about this last section. So the statement that the higher spin fields don't interact is really, like some de Sitter version of Coleman Mandula, or, like, or what is the?
I mean, the de Sitter and also ADS version of Coleman Mandula was actually, I think, done by Malasena and Zhiboedov, where they showed that if you have, like in the CFT, if you have a higher spin conserved current, then the theory is necessarily a free theory. Yes. So that was, I think the same, it was expected that the same would hold also in de Sitter. But our analysis is closest in spirit to extending like the Weinberg analysis of flat space to de Sitter and also in ADS.
Okay. For example, so you talked about the Vasiliev theories, but let's say, like if you consider some kind of string theory in de Sitter, it's not always clear what is a very sharp model to do that, but let's say there's a string theory in de Sitter, which we consider some perturbative string theory, then, would you say that this kind of a statement that we know from a flat space that that the string scattering in a certain limit is soft at high energies? I mean, one like intuitive way of understanding it is that, is this kind of an argument that at high energies, like the string has massive high spin states. At high energies, like this, they're effectively massless, and so things are kind of, they don't interact so much, and so the scattering is soft. So do you think there is that kind of an argument even in de Sitter, that even in something like, if you had something like string theory in de Sitter, can you argue that, I mean, at some limit, the thing should be softer than usual field theories, the correlation functions and so on?
I wouldn't know how to study that on like concretely, but intuition would say yes, but I don't have I don't have any argument to that would like give weight to this statement. No, but I would expect so, yes, but yeah, I don't know.
Okay.
Okay, thanks. Charlotte, let me ask you, I know it's kind of late, but just one or two questions, if you don't mind, which is, don't want to keep going back to this, but anyway, when we did some of our work, the main thing we were interested in a sense in asking was, what's a let's say observationally, they see signals from inflation, which is nearly de Sitter, not quite de Sitter. How would we know that the universe was approximately de Sitter during inflation? You know, and that's sort of why we were thinking about the ward identities which arose out of the symmetries of de Sitter. And I'm just wondering, I know you have this really beautiful analysis. You can just compute the correlation functions directly, very powerful. But just to go back, and as you correctly said, from the de Sitter, you know, say you take the 4-point function, you can replace one external leg by the rolling value of the dilaton and get it, of the inflaton and get a 3-point function out. So you could easily use some of this for inflation. So my question to you is there a telltale, it's a vague question, but is there a telltale signature we can say would really tell us that the universe was approximately de Sitter at the time when the perturbations, the CMBCs, originates? You know, wouldn't that be great if we could say?
Yeah, it would.
But you know, what happened in our work was we tried to make it as model independent by just referring to ward identities. But you know, there is always DBI inflation, which does something, you know, it wasn't smoking gun, you know, in the end, I would say as smoking gun. But I'm wondering, you've done much more, and I'm wondering what you feel.
Gosh, no, I wouldn't know. Yeah, I mean, I haven't really thought about it.
Sorry. No, but I just thought, okay, to put it a little more precisely, and you said this already, but do you think something can be gained, even though you could just compute things without paying too much attention to paying too much heed to ward identities? Do you think there's something to be learned by going back to the ward identities of conformal invariance in your formalism and seeing, you know, in a sense, what's all model independent and what's maybe depends on the details of the contact interactions and the, you know, exchanges? Is there something to be gained there, you feel? Or
I mean, going back to the ward identities.
Yeah.
Always the ward identities is some way incorporated within our framework, right? And then of course, like after you've had these general form that the exchanges should take, you can ask more precise questions, like you said, like for instance, you can focus on interactions which maybe are shift symmetric and so on. So it provides a useful framework that gives a lot of control on these type of parameters in the theory. So I think, the Mellin formalism provides a good setting to explore these questions because you have a lot of control over the form of the correlator and also like studying its analytic properties and so on. So it just provide a useful framework to address this type of things. But I don't have a concrete answer.
No, that's fine. Okay, more question, then I'll stop, which is, you know, at least when we try to think about alpha vacua with Nilay also, take this 4-point function with just graviton exchange. You know, if you take the points on the boundary further apart, the graviton propagator goes deeper and deeper in. Mm-hmm. And in alpha vacua, we found, you know, because they are slightly crazy vacua in that, in a sense, you are exciting lots of modes. You know, there were sometimes divergences. We didn't fully understand them that arose. Sorry?
How did they appear, these divergences?
You know, if you look at this, I think you also had this Poincare time eta or whatever in de Sitter. When eta goes off to past infinity or something, if it's Bunch-Davies, you can, sorry, it's a bit technical, but if Bunch-Davies, it's closely connected to ADS through a I epsilon prescription, and that controls the behavior in the far past, but not so obviously in the alpha vacua. And I'm just asking whether you saw something like this. We didn't do by any means as, you know, control the analysis as you've done, or do you find that all correlators are well behaved in alpha vacua as well? Let's say 4-point functions and so on.
At least, so as I said, all of the concrete examples that we analyzed were for Bunch-Davies. But the way it looks like in our formalism is that these alpha vacua correlators, you can, okay, I haven't looked at it in detail, but to me it looks like that you can express them precisely in terms of exchanges within the Bunch-Davis vacuum. So naively, maybe one indeed would have to be careful when you take this limit e to 0 versus 0. This is something that we haven't been careful about even in Bunch-Davis. But naively, I wouldn't know where this type of issue would arise. But I would have to.
I see. Okay. Yeah. Maybe we'll go back and look.
Yeah, that would be.
My follow-up. Go ahead,
Sorry?
please. No. My follow-up question then for you, and anyway, we can continue this over email or whatever, is, so, let's say the universe was approximately de Sitter at the time the CMB perturbations got generated. How would you know whether it was in a non-trivial alpha vacuum or the Davis? Does as far as I recall, the 2-point correlator, because the alpha vacua preserve the symmetries, right? It preserves I think now maybe I'm rusty, but I think the 2-point function is too crude, if I remember right.
Yeah. How would you check? I mean, the level, so
because,
maybe the one thing that I think would change, but maybe you would do something at a correlator which has a greater chance of being observed, is like at the level of these exchanges. So because how in this squeezed limit you see these sign functions.
Yeah.
The alpha vacua, like if you're in an alpha vacua, the argument of these sign functions would be shifted. So like this affects, like if you had the exchange of a massive particle in de Sitter, then the early time vacuum would change it looks like to me, but I haven't checked properly. And it looks like this alpha vacuum would change the way in which the phase of these oscillations. So if you can observe the phase, then this may give you information about what type of, like what is the vacuum at early times.
Yeah.
Also the kind of the linear, the relative coefficient between these two infinite families of non-analytic terms.
Yeah.
This would also be affected by the choice of early time vacuum.
Yeah.
This is also be another signal. But maybe even at the 3-point level, there is.
Yeah. Where we got stuck, I think Nilay can correct me, is just the graviton exchange. But if that's all controlled, you can just take one of the 4 legs and put the slow roll parameter there, right? So, maybe even, we should go back after your calculation, but if even the 3-point function, which is the leading non-Gaussianity, cares about the alpha parameter, it would be nice to make this concrete a little bit, right? To be able to tell the observers, okay, let's assume it's slow roll inflation, okay? But then if it were an alpha vacuum, this is how you'd measure the alpha parameter. That would be really great, right? Okay.
Yeah, that would be a nice thing. I think that also within our formalism, this is something that is quite doable, at least given what we've done so far.
Okay.
This alpha vacua, like this alpha vacua is like having some particles even in the it's not the vacuum state.
Yeah.
So if there are signatures of having physical particles in your correlation functions, like there was a recent paper in January or something by Green and collaborator, where they were asking the same question, like if I just look at the correlation function, how can I say whether the primordial, the like non-Gaussian, what is the signature that the fluctuations were classical in nature or quantum?
Yeah.
So, if you, for the classical calculation, they did a, stochastic type analysis of the, let's say, 3-point function and probably like, alpha vacua having some real particles in it. Maybe there will be some, singular, this folded singularities, which are like this 1 over K1 plus K2 minus K3, that kind of singularities in the 3-point function at least.
That's precisely right, and you can see that. You can, you can check that if you impose Bunch-Davis vacuum, then you precisely don't have this type of.
Don't have this similarity.
But then Yeah, but then when you go to different vacua, you change this kind of relative coefficient between these non-analytic families that you saw, and this precisely is what generates this type of horrible singularity.
Yeah.
As you say.
Yes.
So just to continue on that, so one way would be to like there was a paper by Daniel Bowman, etc., where they put in this information that whether you have some singularity or not, and using those information they could build a correlation function. So if suppose one wants to get this alpha vacua thing, then one would put in that in a particular limit, one has to have some particular kind of singularity and then try to resolve the problem.
Yes. Yeah, yeah, I mean, now in some ways you can think of our analysis as kind of like extending theirs, but including this extra information. So our...
I mean, there's zero...
Sorry?
Yeah, go ahead. Go ahead, Charlotte. Go ahead.
So like our... When I said that we fixed the de Sitter exchange from boundary conditions, this is precisely their boundary condition. So their boundary condition was requiring the absence of this folded singularity. And we kind of included this freedom in our choice of linear combination of these projectors omega d and omega n. So in allowing more general linear combinations is what is parameterizing your choice of this folded singularity.
I see. But what I'm tempted to do now after your talk, and of course everyone's probably done it, but I is to just go back and do the 3-point function for scalar perturbations. Where I had at least gotten stuck because of, regulating the eta going to 0 behavior. But I want to go back to that just to see in the functional form you get, which Maldacena first computed, right? Famously. Is there, does the alpha parameter enter somewhere? So that, you know the answer by any chance, Charlotte? So that,
what is the object that we're computing again? Sorry.
Sorry, 3-point function for scalar perturbations in inflation. But just to simplify it, it's the 4-point function for massless scalars with graviton exchange, where one leg is replaced by the slow roll back, right? Yeah. And the question is, when you compute that as a function of momenta, you get some functional form. Is there a dependence on the alpha parameter?
Yes, there is a dependence on the alpha. Yeah. So it changed, so it affects. So
sorry, I'm not sure what you want me to change.
So it would you would see that as we discussed in the squeeze limit. So this dependence on the alpha parameter would enter in these relative coefficients alpha and beta of these projectors omega d and omega n. So the first thing that you would have to do is we haven't done it yet, but you would get the general form of these alphas and betas for the propagators in the alpha vacua, and then you would insert this into our expression for the exchange in terms of these general alphas and betas. And so this is how it's encoded in the exchange, and you would see it most clearly in this squeeze limit. So you would see the relative coefficient between these non-analytic terms would depend on these alphas, this alpha parameter.
Okay,
so,
but I mean, one should just work it out in general, the full functional form, which isn't hard to do, I think, given everything you've done, because if they see the non-Gaussianity in the scalar sector, they'll probably be able to see it in more than just the squeeze limit, you hope. So
from our expression, you can get the full thing. It's we're now formally.
It's probably trivial for you, but I think it's important observationally, right? Because because this is one of the only things that the non-Gaussianity in the scalar sector is probably one of the few things they'll measure, in the decade or two, if you're lucky. So it's good to make it clear what is a telltale signal of a non-trivial alpha parameter, right? And then
that would be
and then just anyway, okay. No, that's great. That's great. Thank you. You should also, but it's child's play for you. But anyway, it'll be fun to work on. Okay. Well, it's kind of running late, but if there's a really pressing question, then please ask. Otherwise, let's thank Charlotte for a great talk and really fun talk. Anyone wants to ask something? Okay, well, looks like not. Okay, well, I mean, we are really sorry we can't take you out for a nice Indian meal at the end of this, but really look
nice experience anyway. But yeah, if you're interested to discuss further this stuff on alpha vacuum, please feel free to send both me and Massimo an email, and yeah, it would be really interesting.
We'll definitely try to do something and then write to you with some calculations, yeah, and that'll be fun, or just a chat, yeah.
Yeah.
And it'll be great, and we'll look forward to having you in India sometime so we can really go out and have a good dinner. But anyway, thank you very, very much from all of us for a great talk and for staying so long. Thank you.
Thank
Thanks.
you so much.
Okay, bye.